Subscribe to the channel and like the video. Somewhere, floating quietly in the great halo of our Milky Way, there exists a star so ancient that it nearly predates time itself. Imagine a glowing ember, older than galaxies, older than planets, older than almost everything we can see when we gaze up at the night sky. This star, known simply as SM0313, is not just any ordinary point of light. It is one of the oldest stars ever discovered, a survivor from the dawn of cosmic history. To put it into perspective, it has been shining since shortly after the Big Bang, making it a true fossil from the universe's earliest days. What makes SM0313 even more fascinating is the story it carries in its light. Its existence bridges the unfathomable gap between the violent, chaotic birth of the universe and the rich, structured cosmos we live in today. For astronomers, SM0313 is nothing less than a cosmic time machine. By studying its chemical fingerprint, scientists are able to peer back nearly 14 billion years into the infancy of the universe itself. It is a window into an age when the very first stars were being born and the raw ingredients for galaxies, planets, and eventually life were just beginning to take shape. But before we dive into its chemistry, age, and mysteries, let us properly introduce SM0313 and why it has captured the imagination of astronomers around the globe. SM0313 is often described as one of the most extreme relics of the early cosmos. Found in the outer reaches of the Milky Way, it is not a star you can see with the naked eye. In fact, it's incredibly faint, hiding in the quiet outskirts of our galaxy where few stars shine bright. Yet, despite its unassuming presence, SM0313 holds a status almost unmatched in astronomy. It is older than nearly everything else we know, a witness to the earliest epochs of creation. When astronomers first identified this star, they immediately realized its significance. Not only was it extraordinarily ancient, but its chemical composition was unlike any other. It seemed to contain virtually no iron at all, a feature that made it stand out starkly against all other known stars. This absence of heavy elements marked SM0313 as a relic, untouched and unpolluted by the long history of stellar generations that followed. The very fact that SM0313 is still burning today is a marvel in itself. Most stars born in the earliest epochs were massive, short-lived titans that burned brightly and died violently as supernovae within just a few million years. But SM0313 is different. It is small, quiet, and enduring. A star that has persisted across almost the entire age of the universe, quietly glowing while countless others have lived and died around it. Introducing SM0313 is much like introducing a character from a forgotten epic. It is not flashy or dominant in brightness, but it carries with it a story that outshines nearly everything else in the night sky. Every atom of its makeup, every photon of light it emits, tells us about a universe that was once young, raw, and entirely different from the cosmos we inhabit today. SM0313 may sound like a neat and simple nickname, but behind it lies one of the most intimidatingly technical catalog names you'll ever hear in astronomy. SMSS J031300.36 670839.3. When you first see that written down, it looks more like a computer password than the name of a star. And that's because, in a sense, this designation is a kind of coordinate-based address in the sky, ensuring astronomers know exactly which tiny pinprick of light is being discussed. Let's break it down. The SMSS part at the beginning refers to the SkyMapper Southern Sky Survey, the ambitious project that discovered the star. SkyMapper is a powerful wide-field telescope located in Australia, designed specifically to scan vast swathes of the southern hemisphere's sky in search of rare and unusual celestial objects. Every star identified by this survey receives an official catalog number that encodes its position on the celestial sphere. The rest of the name, J031300.36 670839.3, is essentially a set of celestial coordinates written in the J2000 system, which is a standardized astronomical coordinate system tied to the position of the Earth at the year 2000. The first string of numbers, 31300.36, refers to the star's right ascension, a measure of its east-west position in the sky relative to the celestial equator. The second string, 6700839.3, refers to its declination, the north-south positioning above or below the celestial equator. Put them together, and you have a precise cosmic address that tells astronomers exactly where to point their telescopes to find this faint star among billions of others. But here's the thing, No one wants to say SMSS J031300.36 670839.3 every time they mention the star. Imagine trying to hold a discussion, or worse, deliver a lecture or video presentation, and repeating that tongue twister over and over again. It's simply not practical. That's why astronomers and science communicators quickly adopted the shorthand nickname, SM0313. It keeps the essential parts of the name, SM for SkyMapper, followed by the first few digits of its coordinate-based designation, but strips away the cumbersome detail. In doing so, it provides a balance between scientific accuracy and human usability. This is actually quite common in astronomy. Most stars discovered in large surveys are given long, catalog-based names that encode their origins and positions. For example, quasars, pulsars, and other exotic objects all tend to have string of numbers identifiers. But when one particular object becomes especially important or famous, scientists tend to adopt a more manageable nickname. HD 140283, for example, is often called the Methuselah star because of its extreme age. The pulsar PSRB 1919+21 is simply called the first pulsar ever discovered. And SMSS J031300.36 670839.3 became SM0313, short, simple, and memorable. The nickname also helps emphasize the star's special status. Out of the countless faint stars discovered in the SkyMapper survey, SM0313 stood out immediately as something extraordinary. Giving it a distinct, easy-to-remember identity helps highlight its importance in the broader story of cosmic archaeology. Just by calling it SM0313, astronomers are signaling, this isn't just another entry in the catalogue. This is one of the most ancient stars we've ever found, one of the most extreme examples of an extremely metal-poor star, and one of the best windows we have into the earliest chapters of the universe. Think of it this way, SMSS J031300.36 670839.3 is the official ID card. SM0313 is the nickname that makes it human. Both are technically correct, but only one of them rolls off the tongue when you're trying to capture the imagination of scientists, students, or the general public. It's also worth noting that astronomy catalogues tend to overlap and multiply. A single star may appear in multiple surveys, each giving it a different identifier depending on the telescope or project involved. Without a simple nickname, talking about the same object across different research papers could get confusing fast. By using SM0313 consistently, astronomers ensure that there's no ambiguity about which ancient relic they're referring to. So in the end, SM0313 isn't just a convenient shorthand. It's a symbol of how this star moved from being one of millions of catalogue entries to becoming one of the most celebrated discoveries in modern astronomy. When scientists and science enthusiasts speak of SM0313, they're not just referencing a star. They're invoking a story about the universe's very beginnings, about survival across nearly 14 billion years, and about the powerful tools of modern astronomy that made such a discovery possible. And so, when you hear the name SM0313, remember that behind those 6 characters lies a full coordinate map, a cataloging system, and the recognition that some stars deserve to be remembered not as strings of numbers, but as legends. When we speak of SM0313's age, we are stepping into one of the most awe-inspiring comparisons imaginable, the difference between a single star's lifetime and the lifetime of the universe itself. SM0313 is estimated to be about 13.6 billion years old, while the universe, based on the latest cosmological measurements, is about 13.8 billion years old. That means this star is nearly as old as time itself. To put it in perspective, if we condense the entire age of the universe into a single calendar year, with the Big Bang occurring at midnight on January 1st, SM0313 would have formed before the end of January, while Earth, humanity, and all recorded history wouldn't even show up until the last seconds of December 31st. Think about that for a moment. When SM0313 was born, there were no galaxies like the Milky Way as we know them today, no solar systems, no planets, and certainly no life. The cosmos was still in its infancy, filled mostly with hydrogen and helium gas left over from the Big Bang. Light itself had only been traveling freely through space for a few 100 million years after the fog of the early universe cleared during the epoch known as recombination. The first stars, known as population 3 stars, had just begun to form, burn furiously, and die in cataclysmic explosions. Out of that chaotic period, SM0313 emerged as one of the very next generations, a population 2 star, seeded with just the faintest traces of heavy elements from those first colossal stellar deaths. Its age estimate of 13.6 billion years is extraordinary because it pushes right up against the limits of cosmic history. Scientists use multiple methods to measure the age of the universe, observing the cosmic microwave background radiation, tracking the expansion of galaxies through Hubble's law, and analyzing the abundance of light elements like hydrogen, helium, and lithium. These all converge on a universe about 13.8 billion years old. If SM0313 is 13.6 billion years old, then it must have formed almost immediately after conditions in the young cosmos allowed stars to exist, within roughly the first 100 to 200 million years after the Big Bang. That is staggering, because it means SM0313 isn't just old in the sense that it predates Earth or the Sun. It predates almost everything. When the Sun was born a mere 4.6 billion years ago, SM0313 had already been shining for 9 billion years. That's longer than Earth itself has existed. The Sun, in many ways, is still a middle-aged star, while SM0313 is a true elder, a survivor from a time when the universe was still setting the stage for galaxies, planets, and life. Let's frame this another way. Imagine you are standing at the shore of an infinite ocean, and you scoop up a single grain of sand. That grain represents Earth's entire history, from its formation to today. Now, stretch your imagination to include every grain of sand along that beach, stretching into the horizon. The entire lifetime of Earth is but a speck in comparison to the nearly 14 billion years SM0313 has witnessed. Every empire that rose and fell, every species that lived and went extinct, every human achievement from fire to space travel, all of that happened while SM0313 sat quietly in the galactic halo, unchanged, enduring. Another way to grasp the context is through stellar evolution. Most stars that formed in the early universe were massive and short-lived. They burned through their fuel in a few million years, exploding as supernovae and enriching the cosmos with heavier elements. By contrast, SM0313 is a low-mass star, which burns its hydrogen fuel slowly and steadily. This is the very reason it has managed to survive almost the entire lifetime of the universe. Its age tells us that stars of this kind can truly be cosmic survivors, outliving entire galaxies and epochs. Now, the fact that a star can be so close in age to the universe itself also challenges us to consider the precision of our measurements. Astronomers have to be very careful when estimating the ages of such ancient stars. They use methods such as studying the chemical abundances of elements, particularly radioactive isotopes like thorium and uranium, which act as natural clocks. They also model stellar evolution and compare a star's current temperature, luminosity, and metallicity against theoretical predictions. For SM0313, these careful analyses consistently point toward an age just shy of the universe's own age, meaning it is among the very first stellar survivors ever to have formed. It's worth pausing here to marvel at this. We are looking at a star whose life has spanned almost the entirety of cosmic history. If the universe were a grand epic novel, SM0313 was a character introduced in the prologue, and somehow, against all odds, it is still present in the story today. Its faint light carries with it not only the passage of 13.6 billion years but also the record of how the cosmos began to transform from a simple soup of hydrogen and helium into the complex, life-bearing universe we inhabit. The age context, therefore, makes SM0313 more than just an astronomical curiosity. It is a profound reminder that some things in the universe endure on timescales far beyond human comprehension. It outlived countless cosmic events, the birth of galaxies, the ignition of quasars, the merging of black holes, and the cycles of countless other stars. And yet here it is, still shining faintly in the halo of the Milky Way, as if waiting for us to finally take notice and learn its story. When we talk about SM0313's home, we're not describing a place like our sun's cozy neighborhood, nestled in the spiral arms of the Milky Way among billions of other bright stars, planetary systems, and interstellar clouds. Instead, SM0313 lives in one of the most desolate regions of our galaxy, the galactic halo. This halo is a vast, roughly spherical region surrounding the visible disk of the Milky Way, extending far beyond the bright spiral arms we usually picture when imagining our galaxy. It is a realm of sparse stars, ancient globular clusters, and mysterious dark matter. And it is here, far from the galactic center, that SM0313 quietly drifts. The halo is not a place of glamour. Compared to the star-filled galactic disk, where gas clouds give birth to new stars and spiral arms shine brilliantly, the halo seems almost empty. Its stars are few and far between, and most of them are relics from the very early universe, like fossils preserved in the quiet outskirts. These stars don't participate much in the ongoing story of star formation. They simply orbit silently, following paths dictated by the galaxy's gravity. This is precisely where astronomers expected to find ancient stars like SM0313. Why? Because the halo acts as a kind of cosmic retirement home. The bustling, dynamic disk of the Milky Way constantly recycles material. Stars are born, live, die, and spread new elements into interstellar clouds, which in turn give rise to new generations of stars. That process makes the disk a chemically younger place. In contrast, the halo has been left relatively untouched. Stars that formed early in the galaxy's history often remain there, unpolluted by billions of years of stellar recycling. So, SM0313 orbits in this quiet galactic halo, far from the hustle and bustle of the galaxy's central regions. Its path is likely elongated, plunging it in and out of the galaxy's outer reaches, perhaps sometimes bringing it closer in, but mostly keeping it away from the dense, chemically rich environments near the Milky Way center. These kinds of orbits are typical for halo stars. They are often tilted at strange angles compared to the flat plane of the galaxy's disk, and they can travel immense distances in their long journeys around the Milky Way. Living in the halo has almost certainly played a role in SM0313's survival. In the dense disk of the galaxy, stars are more likely to interact with each other, encounter violent environments like supernova shockwaves, or even be disrupted by massive molecular clouds. But out in the halo, conditions are quieter. SM0313 could go about its slow, steady burning of hydrogen without much disturbance for nearly 14 billion years. In a sense, its isolation has preserved it, much like a rare artifact hidden away in a vault rather than exposed to the chaos of daily life. The halo is also scientifically special because it is thought to be where the Milky Way's story began. The very first stars and star clusters that coalesced around our galaxy billions of years ago are believed to reside there. In fact, the halo likely contains remnants of dwarf galaxies that merged with the Milky Way in its formative years, their stars absorbed into our galaxy's outer shell. Studying stars like SM0313 helps astronomers piece together this history, revealing what the Milky Way looked like before it became the majestic spiral galaxy we see today. From Earth's point of view, SM0313 is faint, far too faint to be seen with the naked eye. Its distance from us makes it invisible without the aid of powerful telescopes. But its faintness is precisely what adds to its allure. It's not a star that shines for attention. Instead, it's a quiet elder living on the outskirts, whose value lies in the secrets it carries. Astronomers often think of the galactic halo as a kind of stellar museum. Every old, metal-poor star within it is like an exhibit, preserving a record of the universe's earliest times. SM0313 is one of the crown jewels of this museum, a piece so rare and precious that it allows us to peer back nearly to the Big Bang itself. By analyzing stars like SM0313 in the halo, researchers can reconstruct the timeline of the galaxy's formation, tracing how the Milky Way grew and evolved. It's also worth noting that halo stars like SM0313 don't orbit neatly around the galactic center the way disk stars do. Our Sun, for example, follows a fairly regular circular orbit within the galaxy's disk, taking about 225 to 250 million years to make one full revolution. SM0313's orbit, however, is likely highly eccentric and tilted, shaped by the chaotic conditions of the early Milky Way and the gravitational tug of dark matter that dominates the halo. It may plunge in toward the galaxy before swinging far back out again, completing orbits that could take billions of years. In short, SM0313's location in the galactic halo is not just a detail about its coordinates in space. It's part of the reason it has survived for so long, untouched and unaltered. Its home in the halo means it has been preserved as a living fossil, a pristine witness to the earliest times in the universe's history. So when we talk about where it lives, we're not just pinpointing its coordinates on a map of the sky. We are acknowledging that SM0313 is a relic of the halo, a region that cradles some of the oldest and most mysterious stars in the Milky Way. It's like finding an ancient, undisturbed manuscript in the attic of a library that has otherwise been rebuilt and renovated countless times. The halo preserves what the rest of the galaxy has long since rewritten. In astronomy, when scientists describe a star as metal poor, they're not talking about gold, silver, or jewelry. They're using a very specific definition of the word metal. In everyday language, metals are things like iron, copper, or aluminum. But in astronomy, everything heavier than hydrogen and helium is considered a metal. That means oxygen, carbon, nitrogen, calcium, even the elements that make up water, air, and our own bodies. All of these count as metals in the astronomer's dictionary. So, when astronomers call a star metal poor, they mean it contains almost no elements heavier than hydrogen and helium. And when they call a star extremely metal poor, as they do with SM0313, they mean it contains so little of those heavier elements that it's practically primordial, nearly identical in composition to the universe just after the Big Bang. To understand why this matters, we need to look at the history of cosmic chemistry. Right after the Big Bang, the universe was astonishingly simple. It consisted almost entirely of hydrogen and helium, with just trace amounts of lithium. No carbon, no oxygen, no iron, no silicon, none of the elements we associate with planets, life, or complex chemistry. Those heavier elements were manufactured later, inside stars themselves. When massive stars formed, they fused hydrogen into helium, and then helium into heavier elements like carbon and oxygen. The most massive stars went even further, creating elements as heavy as iron in their cores. But here's the catch: all of those elements remained locked inside the star until it died. When those first massive stars ended their lives as supernovae, they expelled their enriched guts into the cosmos, seeding the interstellar medium with new elements. That enriched gas then gave rise to new generations of stars, which inherited these metals in their makeup. Over billions of years, this process gradually increased the metallicity, the fraction of heavier elements, in the galaxy. That's why stars can be used as a kind of cosmic family tree. Younger stars, like our Sun, have high metallicity because they formed from gas that had already been enriched by countless previous generations of stars. Older stars, on the other hand, tend to have much lower metallicity, because they were born earlier in cosmic history, before the universe had much time to make and distribute heavy elements. SM0313, though, is in a class all by itself. Its metallicity is so low that astronomers describe it as extremely metal poor, one of the most metal poor stars ever discovered. In fact, when its spectrum was first analyzed, astronomers were stunned to find that it contained virtually no detectable iron. To give you some scale, the Sun contains a certain baseline amount of iron and other heavy elements. SM0313 contains less than 1 part in 10 billion of that iron abundance. It is, in practical terms, iron-free. What it does contain are small traces of a few other elements: carbon, magnesium, and calcium. But even those are present at vanishingly tiny levels compared to stars like the Sun. The absence of metals in SM0313 means it must have formed almost immediately after the very first supernovae went off, at a time when the universe was still chemically primitive. This makes SM0313 a sort of chemical time capsule, a direct messenger from an age when heavy elements were just beginning to appear. The term extremely metal poor is not just an abstract label. It's a key to SM0313's importance. By studying stars with such low metallicity, astronomers can effectively wind the clock backward and reconstruct the conditions of the early universe. Every bit of its spectrum tells us something about what elements were present in the gas cloud that gave birth to it, and therefore what kind of supernova might have seeded that gas in the first place. And here's something that might sound counterintuitive: without metals, it's actually very difficult for stars to form at all. Metals play a crucial role in cooling gas clouds, allowing them to collapse under gravity into compact, star-forming clumps. In the early universe, with no metals to help, gas clouds resisted collapse. That's one reason the first stars, the so-called population 3 stars, are thought to have been extremely massive. They needed sheer size to overcome the difficulty of collapsing from metal-free gas. Those massive stars lived fast, burned furiously, and died young, producing the very first metals in their explosive deaths. SM0313, however, shows us that under the right circumstances, it was possible for low-mass stars to form from gas enriched by just the faintest touch of heavy elements. And because it was low mass, it didn't burn out quickly like its massive predecessors. It lingered. It endured. And now, 13.6 billion years later, it's still here for us to study. So when we describe SM0313 as extremely metal-poor, what we're really saying is that it's nearly pristine. Its chemical makeup is as close as we'll ever get to the raw material of the early universe, just barely touched by the first whispers of stellar alchemy. For astronomers, that makes SM0313 not just an old star, but one of the most scientifically valuable stars in existence. Its lack of metals is not a deficiency, it's a gift, allowing us to peer into a time before the universe was filled with the rich chemistry that eventually led to Earth, life, and us. Stars like SM0313 are often called time capsules of the universe, and that is not just poetic language, it is an accurate description of their role in cosmic history. Unlike galaxies that merge and change shape, or planets that recycle their crusts and atmospheres, or even humans who live for only a fraction of cosmic time, ancient stars preserve their original properties for billions of years. They are like untouched fossils, carrying the imprint of the conditions under which they were born. When we look at SM0313, we are not just observing a star in the present day. We are observing the chemical story of the early universe itself. Its light carries with it the signature of the gas cloud from which it formed, gas that was enriched only slightly by the very first supernovae that ever exploded. That means SM0313 contains a record of the very earliest cycles of star birth and death, back when the cosmos was still fresh from the Big Bang. The universe has no diary, no written record of how things unfolded in its first few 100 million years. What it does have are stars like SM0313. These stars, with their pristine chemistry and incredible ages, act as natural archives. The ratios of elements in their atmospheres tell us how many generations of stars had lived and died before them. Their metallicity tells us how much time had passed since the Big Bang when they were born. And their continued survival allows us to measure these properties today with modern telescopes and instruments. The beauty of this idea is that stars are closed systems. Once a star like SM0313 is formed, it does not significantly change the composition of its outer layers. Its core may be burning hydrogen into helium, but the outer atmosphere, the part we observe when we analyze its spectrum, remains largely unaltered. That means the light we collect from SM0313 today is carrying the exact same chemical information that was locked in nearly 13.6 billion years ago. It's as if nature pressed pause on the conditions of the early cosmos and handed them to us in the form of a living, glowing relic. For astronomers, this is nothing short of miraculous. We cannot go back in time to watch the first stars form. We cannot directly observe what the Milky Way looked like 13 billion years ago with our own eyes. But we can study SM0313 and stars like it. They give us direct evidence of what the early universe was like. Their chemistry reveals what kinds of supernovae occurred at the dawn of time. Their ages tell us how quickly the first galaxies formed. Their positions in the galactic halo help us map out the growth and evolution of the Milky Way itself. Think of SM0313 as a cosmic messenger, carrying a letter across 13.6 billion years of history, sealed and preserved, waiting for us to finally open it. That letter is its spectral fingerprint, the specific absorption lines of elements visible in its light. Each missing or faint line tells us what the early universe lacked. Each visible line tells us what it had just begun to create. By decoding that spectrum, scientists reconstruct not just the history of one star, but the story of an entire era in cosmic evolution. And here's where it becomes even more profound. Without these time capsules, we would be almost blind to the early universe. Yes, we have the cosmic microwave background, which shows us the conditions of the universe just 380,000 years after the Big Bang. And yes, we have galaxies observed by telescopes like the James Webb Space Telescope, peering back billions of years. But stars like SM0313 fill in a crucial gap, the period when the first stars were dying and the first metals were being spread across space. They are our only tangible evidence of what that transition looked like. It's no exaggeration to say that without metal-poor stars like SM0313, our understanding of cosmic history would be incomplete. They are the missing pages of the universe's book, the chapters that tell us how we went from a simple hydrogen and helium cosmos to the chemically rich galaxy capable of producing planets, oceans, forests, and eventually conscious beings. The idea that one faint star in the halo of the Milky Way could carry such a monumental record is both humbling and inspiring. It reminds us that the universe has been keeping careful notes all along. We just had to learn where to look and how to read them. SM0313, as one of the purest and most ancient stars known, is one of the clearest notes of all, a message in starlight whispering across nearly 14 billion years. This is what it was like in the beginning. The discovery of SM0313 in 2014 was not a simple stroke of luck. It was the result of careful planning, powerful technology, and the patient effort of astronomers determined to uncover some of the oldest stars in existence. This story begins in the southern hemisphere, with a telescope designed specifically for surveying the sky in search of rare and unusual stellar relics. The Sky Mapper telescope, located at the Siding Spring Observatory in New South Wales, Australia. Sky Mapper is a 1.35-meter wide-field telescope, but don't let its relatively modest size fool you. What makes Sky Mapper extraordinary is not its diameter, but its purpose. Unlike large telescopes that zoom in on single objects for detailed study, Sky Mapper was built for breadth, to map vast swaths of the sky quickly and efficiently. Think of it as a cosmic census taker, cataloging millions upon millions of stars with the goal of finding the few hidden gems that don't look like the rest. By 2014, Sky Mapper was conducting the Sky Mapper Southern Sky Survey, an ambitious project to systematically observe the southern sky in multiple filters. Among the goals of this survey was the search for extremely metal-poor stars. Astronomers knew that somewhere out there, hidden among the billions of ordinary stars, there had to be survivors from the early universe. These ancient stars would stand out because their light would lack the telltale fingerprints of heavy elements. The challenge was finding them in the first place. To identify candidates, astronomers used clever techniques. They relied on photometry, the measurement of starlight in different color bands, to look for stars whose colors hinted at unusual chemical compositions. Stars rich in metals absorb light at certain wavelengths, making their colors appear slightly different than stars without metals. By filtering through millions of stars this way, Sky Mapper's survey team could flag potential metal-poor candidates for closer study. That's how SM0313 was first noticed. At first glance, it seemed like an unremarkable, faint star tucked away in the galactic halo. But its photometric profile suggested something strange. It might lack nearly all heavy elements. This immediately caught the attention of astronomers, because if true, it would make SM0313 one of the purest and most ancient stars ever discovered. To confirm their suspicion, astronomers needed to go beyond photometry and obtain spectroscopy. While photometry can give broad hints about a star's composition, spectroscopy provides the detailed fingerprint, the absorption lines that reveal exactly what elements are present in the star's atmosphere. For this, the team turned to one of the world's premier astronomical instruments, the Magellan telescopes in Chile, located at Las Campanas Observatory. The high-resolution spectroscopic observations were jaw-dropping. When astronomers examined SM0313 spectrum, they expected to see faint iron lines, even in a very old, metal-poor star. But SM0313 showed nothing. Its spectrum contained no detectable iron at all. Instead, it displayed only faint traces of carbon, magnesium, and calcium. This was unprecedented. No star ever observed had shown such a complete absence of iron lines. The discovery was so surprising that astronomers at first had to double-check their methods. Had the instruments malfunctioned? Was the data processed incorrectly? But repeated observations confirmed it. SM0313 truly contained less iron than any other star known, less than 1/10,000,000th the amount found in the Sun. This made it not only a remarkable find but also a crucial data point in understanding the earliest epochs of star formation. In 2014, the discovery was formally announced in the journal Nature, and SM0313 immediately became a headline in the astronomical community. It was celebrated as a living fossil star, a relic from just after the Big Bang, and a confirmation that low-mass stars could indeed form in the universe's earliest days. For the first time, astronomers had in their hands a star that seemed to have been seeded by only one of the very first supernovae. A single, faint explosion that sprinkled the bare minimum of elements into the gas cloud that would one day condense into SM0313. The discovery also showcased the power of the SkyMapper survey itself. By building a telescope dedicated to finding rare stars, astronomers had struck gold, or in this case, the absence of gold, iron, and almost everything else. SM0313 proved that the strategy worked, and it paved the way for the discovery of more extremely metal-poor stars in the years to come. It's worth reflecting on how improbable this is. Out of hundreds of billions of stars in the Milky Way, SM0313 is just one tiny, faint point of light. It does not shine brightly, it does not dominate its surroundings, and it would never catch the eye of a casual stargazer. Yet through the careful, methodical work of astronomers scanning the sky with SkyMapper and then confirming their findings with world-class telescopes, this one faint star became one of the most significant astronomical discoveries of the 21st century. SM0313 reminds us that sometimes the most profound cosmic truths are hidden in the faintest, most unassuming corners of the sky. It took the right tools, the right strategy, and the right curiosity to find it. And once it was found, it transformed from an anonymous flicker into a beacon of knowledge about the dawn of the cosmos. When SM0313 first appeared in the data, it didn't stand out because it was bright or beautiful or in any way visually striking. Quite the opposite, it's faint, tucked away in the halo of our galaxy, invisible to the naked eye. What made it stand out, what made it leap off the page of astronomical data, was what wasn't there. When astronomers look at stars, they often use spectroscopy, which is essentially the science of breaking down a star's light into its component wavelengths, like passing sunlight through a prism and revealing a rainbow. Within that rainbow are tiny dark lines known as absorption lines. These lines form when specific elements in the star's atmosphere absorb certain wavelengths of light. Each element has its own distinct fingerprint, a set of absorption lines at very specific places. By reading these lines, astronomers can figure out which elements are present in the star, and in what amounts. For most stars, even ancient ones, one set of lines is almost always visible: iron lines. Iron is one of the most common heavy elements in stars, produced abundantly in the cores of massive stars and released during their supernova deaths. Even in very old, metal-poor stars, astronomers can usually detect faint traces of iron in the spectrum. The lines may be weak, but they're still there. But when SM0313 spectrum was examined, something extraordinary happened. The iron lines were missing. Completely absent. The star's light looked strangely bare, stripped down, lacking the usual fingerprints astronomers are accustomed to seeing. It was as if SM0313 was telling the universe's story with entire chapters missing, the chapters where iron and other heavy metals normally appear. This was unprecedented. No star ever observed had shown such a complete lack of iron. Even among the most metal-poor stars known at the time, faint iron lines could still be detected. SM0313, by contrast, appeared to contain less than 1/10 the amount of iron found in the Sun. To put that into perspective, if the Sun's iron content were represented by a full swimming pool of water, SM0313 would have less than a single droplet. This absence made the star instantly remarkable. It wasn't just another old, metal-poor star. It was in a category of its own. It forced astronomers to confront a new reality. Stars could exist with almost no trace of iron, surviving across nearly 14 billion years. And because of that, SM0313 became one of the most valuable time capsules in the universe, preserving the conditions of a cosmos barely touched by the cycle of stellar birth and death. The lack of iron also raised fascinating scientific questions. If SM0313 had so little iron, what kind of environment had it formed in? What kind of supernova could have seeded the gas cloud with just enough carbon, magnesium, and calcium to form a star, but almost no iron? Its spectrum didn't just surprise astronomers, it puzzled them, challenged them, and pushed them to rethink their models of the early universe. What's remarkable is that it wasn't the presence of something spectacular that made SM0313 unique. It was the absence of iron. The silence in its spectrum spoke louder than the presence of any element could have. That silence told astronomers that they were looking at a relic from a time before the universe had widespread heavy elements. In effect, SM0313's missing iron lines shouted across the cosmos, "I was born before the universe was rich in metals. I carry the signature of the dawn." This discovery also highlighted the power of modern astronomy. Without sensitive spectroscopic instruments, SM0313 would have blended in as just another faint star among billions. But with the right tools, astronomers could peel back its layers and discover that it was not ordinary at all, but one of the most extraordinary stars ever found. SM0313 stood out not because it dazzled our eyes, but because it rewrote our understanding of the early universe. Its missing iron lines weren't just a curiosity, they were a revelation, a direct link to the time when the first stars exploded and seeded the cosmos with its very first elements. When scientists describe SM0313 as lacking iron, they're not exaggerating. They mean it in the most literal and extreme way possible. This star contains less iron than any other star ever observed. In fact, its iron content is so vanishingly small that astronomers had difficulty even placing a number on it. Their measurements showed that SM0313 has less than 1 part in a billion of the Sun's iron abundance. That is an almost incomprehensible difference. To put this into a more relatable scale, imagine the Sun's iron content as being equivalent to a massive Olympic-sized swimming pool filled with water. In that analogy, SM0313's iron would be no more than a single tiny droplet, so small that if you blinked, you'd miss it. That is how stark the difference is between our middle-aged, metal-rich Sun and this ancient survivor from the dawn of time. This makes SM0313 not only metal-poor but unparalleled in its deficiency of iron. Other extremely metal-poor stars had been discovered before 2014, but even those stars contained detectable iron in their atmospheres. SM0313 broke the record, standing in a league of its own, with effectively no measurable iron at all. It was as though the universe had handed astronomers a relic from an age when iron simply did not exist in meaningful amounts. But why iron? Why is this element in particular so important? Iron is a cornerstone in stellar astronomy for several reasons. First, it is one of the most stable elements that can be produced inside stars. When massive stars reach the end of their lives, they build up layers of heavier and heavier elements in their cores through nuclear fusion. But fusion stops at iron. That's because fusing iron consumes more energy than it produces, making it the end of the road for stellar nuclear burning. Once a massive star's core becomes iron-rich, collapse and supernova are inevitable. Because of this, iron is one of the most abundant heavy elements released in supernova explosions. Over billions of years, supernovae scattered iron across the galaxy, enriching the interstellar medium and ensuring that younger stars like our Sun were born with plenty of it. That's why most stars, no matter how old, still show detectable iron in their spectra. Iron is a kind of cosmic signature of how many stellar generations have come before. SM0313, however, completely defied expectations. The absence of iron in its spectrum told astronomers something remarkable. The gas cloud that gave birth to this star had not been seeded by multiple supernovae, but likely just a single, unusual explosion. And it must have been a very specific kind of supernova, one that released carbon, magnesium, and calcium, elements that SM0313 does contain, but almost no iron. This revelation hinted at a previously unconsidered class of faint, early universe supernovae, whose unique chemical yields could explain SM0313's bizarre fingerprint. In other words, the missing iron was not a mistake, not an observational error, but a clue. It was a piece of evidence that the earliest stars did not all die in the same way. Some may have exploded violently, scattering iron everywhere, while others may have collapsed more quietly, releasing only lighter elements. SM0313 was living proof of this possibility. For astronomers, this was thrilling, because it meant they could use stars like SM0313 to directly test theories of the first stars and their deaths. Instead of relying purely on computer models or indirect evidence, they had a real, physical star in their telescopes, a star that had faithfully preserved the chemical memory of an event that happened more than 13 billion years ago. So when we say SM0313 contains less iron than any star ever observed, we're not just rattling off a record-breaking statistic. We're describing a cosmic puzzle piece, a data point that forces us to rethink the earliest chapters of star formation. Its missing iron is a fingerprint of a unique type of primordial supernova, one that didn't behave the way we thought. In fact, some scientists argue that without stars like SM0313, we wouldn't even know these faint, iron-poor explosions existed. It is humbling to realize that the lack of something, the absence of iron lines in a faint halo star, could tell us so much about the origins of the cosmos. The silence in SM0313 spectrum speaks louder than any signal. It says, "I was born before the universe was rich in iron. My parents' supernova was not like the ones you know today. I am a child of the first fires." While SM0313 is legendary for what it doesn't have, iron, it is equally fascinating for the handful of elements it does contain. Though astronomers scoured its spectrum for heavy metals and found virtually nothing, they did detect very faint but unmistakable traces of certain lighter elements: carbon, magnesium, and calcium. These are the three key voices that emerge from an otherwise silent stellar spectrum, and they tell us volumes about how this ancient star was born and what it remembers about the universe's earliest days. Let's begin with carbon. The presence of carbon in SM0313 is particularly intriguing. Even though the star is devoid of iron and other heavy elements, its spectrum shows relatively strong carbon features, far more than astronomers expected given its iron scarcity. This makes SM0313 a carbon-enhanced metal-poor star, or CEMP star, a rare subclass of ancient stars that carry disproportionately high amounts of carbon. But why carbon? Carbon is one of the first heavier elements forged inside stars, created through the triple alpha process when three helium nuclei fuse together. In the earliest generations of massive stars, carbon would have been one of the first products of nucleosynthesis to escape into the cosmos. The fact that SM0313 is carbon-rich while being iron-poor suggests that the supernova that seeded its birth cloud released carbon abundantly but retained or swallowed much of its iron. This is one of the main reasons astronomers believe SM0313 was born from the ashes of a faint, primordial supernova, one that did not eject all of its heavier elements evenly. Instead, it spilled carbon into space while trapping iron in its collapsed core. That carbon later became incorporated into the cloud that condensed into SM0313. Next is magnesium. Magnesium is another fascinating element in SM0313's spectrum. It is an alpha element, forged through the fusion of helium nuclei in the cores of massive stars. Magnesium is usually produced in abundance during the explosive deaths of such stars. The fact that SM0313 contains magnesium but still lacks iron adds more weight to the theory of a faint supernova origin. Unlike iron, magnesium can be created in significant amounts even in explosions where the core material, the iron, falls back into a black hole rather than being ejected into space. The magnesium lines in SM0313 spectrum tell us that the progenitor star that preceded it was massive, powerful, and capable of leaving behind these lighter, alpha-rich elements. Finally, there is calcium. Calcium is another alpha element, often produced alongside magnesium. In most stars, calcium is accompanied by significant amounts of iron, but SM0313 breaks this pattern. Its calcium features are present, though weak, standing out in an otherwise barren spectrum. This again signals that the star's parent supernova didn't behave like typical later explosions. Calcium is usually tied to the outer layers of a star, while iron forms deeper within the core. If the explosion was faint or asymmetric, the outer layers, carrying calcium, could have been ejected into space while the inner iron-heavy material collapsed inward and never escaped. Taken together, these three elements, carbon, magnesium, and calcium, paint a vivid picture of SM0313's origin. They tell us it was not born from a chemically diverse environment enriched by multiple generations of stars. Instead, it formed from material polluted by a single, unique explosion, most likely a first-generation star that died quietly, spilling only its lighter fusion products into the void. It's important to pause here and appreciate how extraordinary this is. Astronomers are essentially reading the death signature of a star that exploded over 13 billion years ago by studying the faint traces of elements in another star that survived. SM0313 doesn't just tell us about itself. It's like a messenger carrying the last will and testament of one of the universe's very first stars. The odd balance between what SM0313 does have and what it lacks also reveals a deeper truth about the early universe. Chemical enrichment was messy, uneven, and full of surprises. The first stars didn't all explode in the same way, nor did they scatter their elements evenly. Some seeded the cosmos with iron, while others, like the progenitor of SM0313, left almost no iron at all but did release lighter elements. This patchwork of elemental enrichment eventually built up into the chemically rich galaxies we see today. In other words, Carbon, magnesium, and calcium in SM0313 aren't just numbers on a chart. They're signposts pointing back to the chaotic, experimental chemistry of the infant cosmos. Without them, SM0313 would just be a featureless, iron-empty star. With them, it becomes a living relic that carries within it the story of one of the first supernovae to ever explode. When we look at SM0313, we aren't just looking at an old star, we're staring at the fossil record of an ancient supernova. Its unusual chemical composition is like a fingerprint, and that fingerprint leads us back to a cataclysmic event in the earliest days of the cosmos, the death of a first-generation star. The story begins with the so-called population 3 stars, the very first stars to ever ignite after the Big Bang. These giants were forged from pure hydrogen and helium, with not a single atom of heavier elements. Because they were so massive, often tens or even hundreds of times the mass of the Sun, they lived extremely short lives, burning brightly for just a few million years before exploding as supernovae. Each of these explosions scattered the very first metals, in astronomical terms, all elements heavier than helium, into the young universe, enriching the gas that would later condense into the next generation of stars. SM0313, however, shows us that not all of these early supernovae behaved the same way. The peculiar balance of its chemistry, rich in carbon, magnesium, and calcium, yet utterly devoid of iron, suggests that it formed from the ashes of a very special kind of supernova. Astronomers believe its progenitor was a massive population 3 star that exploded in what's called a faint supernova. Unlike typical core collapse supernovae that release tremendous amounts of iron and other heavy elements, a faint supernova would have ejected mostly the lighter fusion products, such as carbon and magnesium, while much of the iron-rich material fell back into the star's collapsed core. In other words, the explosion wasn't powerful enough to blast all of its interior into space. Instead, it spilled only the outer layers and swallowed the rest, likely forming a black hole in the process. This theory elegantly explains SM0313's bizarre chemistry. Its parent cloud was seeded only with the lighter elements from the progenitor's outer layers, not the heavier ones from its core. That's why SM0313's atmosphere shows carbon, magnesium, and calcium, but less than 1/1000th the iron abundance of the Sun. Think about how profound this is. By studying a tiny, faint star orbiting in the halo of the Milky Way, astronomers are essentially reconstructing the death throes of a star that lived and died over 13 billion years ago. SM0313 is the living legacy of that explosion, preserving in its very atoms the story of how the first supernovae sculpted the universe. Even more fascinating, SM0313's existence supports the idea that not all population 3 stars enrich their environments in the same way. Some may have seeded space with large amounts of iron, setting the stage for more metal-rich stars, while others, like the one that created SM0313, left behind unusual, iron-poor chemical signatures. This variety in chemical fingerprints gives us insight into the diversity of the first stars and their explosions. And the implications stretch even further. If SM0313 was indeed born from the remains of a single faint supernova, it means stars like it are direct observational links to the very first stellar deaths. They act as messengers, whispering across billions of years, this is how the first stars lived. This is how they died. This is how they began to build the elements that would one day become you. It's awe-inspiring to realize that without these first supernovae, the universe would never have produced the raw materials for planets, oceans, DNA, and life itself. Every atom of calcium in our bones, every atom of iron in our blood, was once forged in the heart of a star. SM0313 shows us a snapshot of that process right at its beginning. A universe where iron was almost non-existent, where only the first sparks of heavier chemistry were beginning to emerge. So when astronomers say SM0313 was seeded by a first-generation supernova, they mean that this faint, ancient star was born out of the ashes of the very first cosmic fireworks shows, explosions that transformed a bland universe of hydrogen and helium into a chemically complex one. SM0313 is not just old, it is a direct descendant of the very first stars, a child of the universe's earliest supernovae, still glowing billions of years later. When astronomers talk about the age of stars and their relationship to the history of the universe, they often frame the discussion in terms of stellar populations. This classification system, population 1, 2, and 3, isn't about where the stars live but about when they were born, what they are made of, and how enriched their gas clouds were with elements beyond hydrogen and helium. It's like a family tree of the cosmos, tracing ancestry through the chemistry of starlight. SM0313 plays a fascinating role in this framework because it sits right on the boundary between what we know and what we can only imagine. Let's start with population 1 stars. These are the youngest stars, the ones we see in the spiral arms of galaxies like our own Milky Way. The Sun is a textbook example. Population 1 stars are rich in metals. In astronomical language, metals mean any element heavier than helium. That includes iron, oxygen, carbon, and even rarer elements like gold and uranium. These stars are born from gas clouds that have been enriched over billions of years by countless generations of supernovae and stellar winds. Because of this long chemical recycling process, population 1 stars contain everything needed to form complex planetary systems and, eventually, life. In a sense, they are the children of a long lineage of cosmic evolution. Then we have population 2 stars. These are much older, formed early in the history of the universe, before the interstellar medium had been thoroughly enriched with heavy elements. They contain some metals, but far less than population 1 stars. Many population 2 stars are found in the galactic halo or in globular clusters, those ancient spherical swarms of stars that orbit galaxies like bees around a hive. Their low metallicity makes them excellent timekeepers of cosmic history, because their chemical makeup preserves the conditions of the gas clouds that existed in the young universe. SM0313 belongs in this group, but with a twist, because its metallicity is so low it's practically brushing up against the next, more mysterious category. That category is the legendary population 3 stars. These are the holy grail of astrophysics. They were the first stars ever formed after the Big Bang, born from pure hydrogen and helium. With no metals at all, they were fundamentally different from the stars we know today. Theoretical models suggest they were enormous, many times more massive than the Sun, and short-lived, burning out in a few million years before exploding in violent supernovae. None of them are alive today. They've all long since died. And to date, no population 3 star has ever been directly observed. Their existence is inferred only from theory and from the chemical fingerprints they left in later stars, stars like SM0313. So where does SM0313 fit into this grand scheme? It's not a population 3 star itself, because it does contain some metals, carbon, magnesium, and calcium. But its iron deficiency is so extreme that it almost feels like a population 2 star born directly in the aftermath of a population 3 explosion. In other words, SM0313 is one of the oldest and most chemically pristine population 2 stars we've ever found, practically a bridge between the imagined population 3 and the observed population 2. Its chemistry provides the most compelling indirect evidence that population 3 stars really existed. Because SM0313 could only have formed from a gas cloud touched by a first-generation supernova, its very presence confirms that those primordial giants lived, died, and seeded the cosmos with their first faint sprinklings of elements. Without stars like SM0313, population 3 would remain purely theoretical. With it, astronomers can point and say, here is the child of one of the very first stars. This population framework is one of the most powerful tools in galactic archaeology. By studying which stars belong to which population, scientists can reconstruct the timeline of the universe's chemical evolution, how it went from a barren soup of hydrogen and helium to a vibrant cosmos filled with planets, oceans, forests, and intelligent beings. SM0313 sits at the very beginning of this story, closer than almost any other known star to the original population 3 parentage. SM0313 may be one of the strangest stars we've ever studied, but in terms of classification, astronomers place it firmly within the ranks of population 2 stars. This distinction is critical, because while population 3 stars are the mythical first generation, the giants that forged the very first heavy elements, none have survived to this day. Population 2 stars, however, have survived, and they serve as the next best thing, direct witnesses to the immediate aftermath of the first stars. Let's unpack what that means. Population 2 stars, unlike the metal-rich population 1 stars we see in the Milky Way spiral arms today, were born from gas clouds that had only a trace amount of enrichment from earlier stellar explosions. Their metallicity is low, because only one or a few population 3 supernovae had seeded their birth clouds with elements beyond hydrogen and helium. That's why astronomers call them metal-poor stars. SM0313 is a shining, though faint, example of this. It isn't pristine like a population 3-star would be, but it's about as close as we can get. Its gas cloud had just enough chemical seasoning from an earlier explosion to give it a whisper of carbon, magnesium, and calcium, but not the iron, nickel, or heavier elements that would characterize later generations. In this sense, it's like a newborn child whose ancestry can be traced directly to a single parent, a lone population 3 progenitor. So why is this classification important? Because population 2 stars act as time capsules, preserving the story of the universe between the Big Bang and the era of galaxy formation. They carry in their chemistry the fingerprints of the first supernovae, and their extreme ages mean they formed when the universe itself was still in its infancy. When astronomers study stars like SM0313, they aren't just measuring spectra, they're deciphering the autobiography of the cosmos. SM0313's particular brand of population 2 is extreme. Most population 2 stars still show measurable amounts of iron and other metals, albeit in smaller quantities than the Sun. SM0313, however, is so deficient in iron that it redefines the boundaries of what population 2 can mean. It's essentially a population 2 relic at the very edge of metal poorness, a survivor from a time when the periodic table was still being written by the universe. What's more, being a population 2 star also explains its longevity. Unlike massive population 3 stars that burned out in just a few million years, SM0313 is a low-mass population 2 star. Its lower mass means it burns its hydrogen slowly and steadily, like a candle on its lowest flame. This allows it to endure for billions of years, outlasting nearly every other trace of the early universe. In fact, it's because SM0313 is not a population 3 giant but rather a population 2 dwarf that we can see it at all today. Had it been born bigger, it would have died long ago, leaving behind only a black hole or supernova remnant. So, SM0313 is a population 2 star, one of the very first generation of long-lived stars ever created. It sits just one step removed from the primordial population 3 giants. Its existence is proof that after the violent fireworks of the universe's first stars, quieter, humbler stars emerged, stars that could live long enough to reach across cosmic time and shine into our telescopes today. This classification cements SM0313's role not just as an astronomical curiosity, but as a cornerstone of our understanding of stellar evolution. Without population 2 stars like it, we'd have no direct observational evidence of what the early universe looked like after the first stars had lived and died. To truly appreciate SM0313's place in the cosmos, we need to roll back the clock, way back, to the dawn of time itself. Imagine the universe just after the Big Bang, roughly 13.8 billion years ago. At first, there were no stars, no galaxies, and certainly no planets. Instead, the universe was a hot, dense soup of fundamental particles. As it expanded, it cooled, and about 380,000 years later, electrons and protons combined to form the first neutral atoms of hydrogen and helium. This era, known as recombination, gave rise to the cosmic microwave background, the faint afterglow we can still detect today. But even then, the cosmos was still dark. No stars had yet ignited. This was the so-called cosmic dark ages, a long stretch when hydrogen and helium gas filled the universe, slowly clumping under the pull of gravity. For nearly 100 million years, the universe was starless, silent, and pitch black. Then, gravity began to do its magic. Tiny fluctuations in density, seeds planted by quantum variations during inflation, caused some regions to draw in more matter than others. These clumps grew, and the densest of them collapsed into the first stars. These were the population 3 stars, massive, luminous giants that ignited within 100 to 200 million years after the Big Bang. They burned brightly, lived briefly, and died violently, polluting the pristine gas with the first heavy elements. SM0313 belongs to the very next chapter of this story. It likely formed within that same window of 100 to 200 million years after the Big Bang, when the universe was still less than 2% of its current age. That makes it one of the oldest surviving stars we have ever observed. Think about that. SM0313 has been shining for over 13.6 billion years. When it was born, the universe had just transitioned from darkness to light. Galaxies, as we know them, didn't yet exist. The Milky Way, which it now orbits in its halo, was still billions of years away from forming. What existed instead were primitive proto-galaxies, small, irregular clumps of gas and stars that would later merge to form larger galaxies. SM0313 was likely born inside one of these early building blocks, which eventually merged into the Milky Way we inhabit today. This timeline also highlights just how close SM0313 is to the birth of everything. If the universe is 13.8 billion years old and SM0313 is 13.6 billion years old, that means it formed just a couple hundred million years after time itself began. To put that into perspective, if the universe's entire history were compressed into a single calendar year, with the Big Bang at midnight on January 1st and today at the stroke of midnight on December 31st, then SM0313 would have formed sometime in mid-January. In other words, it's been around for almost the entire cosmic year. Its survival across all that time is almost miraculous. It has endured through the formation of the Milky Way, the merging of galaxies, the birth and death of countless stars, and the rise of planets and civilizations. It was there when the first galaxies lit up the universe. It was there when our sun was born just 4.6 billion years ago. And it's still there now, quietly orbiting in the galactic halo, a fossil from the dawn of creation. The fact that SM0313 formed so soon after the Big Bang makes it one of the most valuable objects of study in the night sky. By examining its chemical composition, astronomers get a direct glimpse of what the universe looked like in its infancy, before it had been heavily enriched by stellar generations. Without stars like SM0313, the window into those early centuries of the universe would be almost completely closed. When astronomers first examined SM0313 in detail, they weren't just looking at a star, they were peering into a kind of cosmic crime scene, with the star itself holding the evidence. Its chemistry is the fingerprint left behind by the very first supernovae. To understand why, we need to think about how stars imprint their signatures on the next generation. Every star is born from the gas and dust surrounding it. The chemical ingredients of that gas come directly from whatever stars lived and died before it. This means every star carries within its atmosphere the fingerprints of its ancestors. If a previous star exploded as a violent supernova, the elements scattered into the surrounding space become part of the recipe for the next star. By measuring what's inside SM0313, astronomers are effectively doing forensic science on the early universe. So what did they find? Unlike almost every other known star, SM0313 has virtually no iron. Its iron content is so minuscule that it is less than 1 part in a billion compared to the Sun. That's astonishing, because iron is one of the most common products of typical supernovae. Instead, SM0313 spectrum revealed high amounts of carbon, magnesium, and calcium. This strange imbalance is the key clue. The chemistry tells us that SM0313 was not seeded by a normal, massive supernova, the kind that would spew out iron and other heavy elements. Instead, it seems to have formed from the ashes of a very unusual kind of explosion, sometimes called a faint supernova. In these events, the star collapses and much of its heavy elements, especially iron, fall back into the core to form a black hole. Only the lighter elements, like carbon and magnesium, are expelled into space. This theory explains why SM0313 is so rich in carbon yet almost devoid of iron. It's the chemical fingerprint of a faint, early supernova, perhaps from a population 3 star that lived fast, died young, and seeded just enough elements to form SM0313. The ratio of elements is like a signature scrawled across time. This is the kind of star that came before me. And what a powerful signature it is. With this evidence, astronomers can reconstruct details of a star that no longer exists, one of the very first stars to ever shine. That's the power of galactic archaeology. SM0313 is like a fossil bone dug up from the sands of time, except instead of telling us about dinosaurs, it tells us about the very first generation of stars. This chemical fingerprint also helps astronomers refine their models of the early universe. For decades, scientists have debated what the first supernovae might have looked like. Were they extremely violent, spewing out every element from carbon to uranium? Or were they faint, selective, and uneven in what they expelled? SM0313 provides one of the clearest answers yet. At least some of those first stars died quietly, enriching the cosmos with light elements but keeping the heavier ones locked away in their cores. The implications ripple outward. Without iron, The cloud that birthed SM0313 was chemically primitive. This star's very existence shows how the first threads of chemical complexity were woven into the cosmos, not all at once, but in uneven bursts, dictated by the deaths of the very first stars. So SM0313's chemistry is not just a curiosity. It's a direct record of the first link in the chain of cosmic evolution. It tells us how the first stars lived, how they died, and how they passed the torch to the next generation. Without stars like SM0313, this entire story would be hidden from us, buried in time. One of the most extraordinary facts about SM0313 is not just when it formed, but that it's still here at all. To survive for 13.6 billion years, nearly the entire lifetime of the universe, a star must have a very particular set of characteristics. SM0313 embodies those perfectly. It is what astronomers call a low-mass survivor. Here's why that matters. Stars are essentially giant fusion reactors. They take hydrogen atoms, fuse them into helium, and release energy in the process. The rate at which this happens depends almost entirely on the star's mass. The more massive a star is, the stronger its gravity, the higher its core pressure and temperature, and the faster it burns. Through its hydrogen fuel. Massive stars live fast and die young, exhausting their fuel in only a few million years before exploding as supernovae or collapsing into black holes. Low-mass stars, on the other hand, are cosmic misers. They sip their fuel instead of guzzling it, stretching out their lives across billions, even trillions, of years. The Sun, with about 1 solar mass, has an expected lifetime of roughly 10 billion years. But stars significantly smaller than the Sun, like SM0313, burn their fuel so slowly that their lifetimes can vastly exceed the current age of the universe. SM0313 fits squarely into this second category. It is a low-mass population 2 star, likely less than 0.8 times the mass of the Sun. Because of this, its core is cooler, its fusion rate slower, and its lifespan extraordinarily long. In fact, SM0313 may not even be halfway through its life yet. It will continue to shine quietly for many billions of years more, long after the Sun has expanded into a red giant and burned the Earth to ash. This slow-burning nature is precisely what has allowed SM0313 to act as a time capsule for astronomers. Had it been a massive star, it would have died in the first few 100 million years after the Big Bang, and we'd have no record of it today. Instead, by being small and steady, it has endured across cosmic history, carrying the fingerprints of the early universe into our modern telescopes. Think of SM0313 like a candle burning on the lowest possible setting. While brighter candles blaze out quickly, this one lingers, dim but persistent, surviving storms, ages, and upheavals. It has witnessed the birth of galaxies, the assembly of the Milky Way, and the rise of life on Earth, all without burning itself out. What's even more fascinating is that this isn't unique to SM0313. Many low-mass population 2 stars are still around, scattered through the galactic halo. But SM0313 stands out because it is so metal-poor, and therefore so much closer in age and composition to the very beginning. In a sense, it's the perfect combination: ancient birth, unusual chemistry, and a body plan designed for survival. The survival of low-mass stars like SM0313 also has profound implications for the far future of the universe. When the more massive stars have long since died, and even galaxies have begun to thin out, low-mass stars will remain, glowing faintly as some of the last lights in the cosmos. In the grand timeline of existence, stars like SM0313 are not just relics of the past, they are also the caretakers of the future. So, SM0313 endures because of its small size, low fuel consumption, and extreme efficiency. It is a survivor by design, a star whose quiet persistence has allowed it to bridge the gulf between the universe's earliest days and our present moment. And it may still be around billions of years from now, a living fossil shining on in a cosmos that looks nothing like it does today. If SM0313 is the patient, enduring elder of the cosmos, then its ancestors, the massive early stars, were the wild, short-lived titans that set the stage for everything that followed. To really understand SM0313's significance, we have to place it side by side with those giants that came before. The contrast between the two could not be more dramatic. The first stars, the legendary population 3 stars, were very different from SM0313. Born out of pure hydrogen and helium, with virtually no heavier elements at all, they had little way to cool their gas clouds efficiently during formation. This meant that the stars that did form tended to be enormous, hundreds of times the mass of the Sun. Some estimates suggest that the very first stars could have reached 200, 300, or even more solar masses. And with great mass comes a great appetite. These massive stars burned their nuclear fuel at an extraordinary pace. Instead of lasting billions of years like SM0313, they lived only a few million years, the cosmic equivalent of a firework bursting and vanishing almost instantly. Their cores became raging furnaces, fusing hydrogen into helium, helium into carbon, and rapidly working their way up the periodic table until they could no longer sustain themselves. At that point, they collapsed and exploded as supernovae or even hypernovae, events so energetic that they seeded entire regions of the universe with newly forged elements. This is where the contrast really sharpens. SM0313's survival owes itself to its modest mass, less than the Sun's, allowing it to sip its fuel slowly. But the massive early stars burned like torches in a hurricane, consuming themselves at breakneck speed. Where SM0313 has survived nearly 14 billion years, these massive stars didn't even make it out of the universe's infancy. By the time SM0313 was taking shape, many of its predecessors were already gone, their ashes strewn across space. The difference in outcomes is profound. Those massive stars are gone forever, but they left their fingerprints behind in the form of the chemical elements they produced. SM0313 is one of the direct recipients of that enrichment. Its carbon and magnesium content almost certainly came from such an ancestor's explosion. In other words, the short, violent lives of massive stars paved the way for the long, quiet lives of survivors like SM0313. Another way to think about this is in terms of cosmic legacy. The massive stars were like trailblazers. They lit up the dark universe, reionized the hydrogen gas, and filled the cosmos with the first metals. But they burned out so fast that they could never witness what came after. SM0313, on the other hand, has endured to carry the story forward. It didn't just form from the ashes of those titans, it has lived to tell their tale, encoded in its chemistry. We can also compare their end states. A massive star might go supernova, collapse into a black hole, or leave behind a neutron star. Its life is defined by violent beginnings and catastrophic endings. A low-mass star like SM0313, however, will never go supernova. Instead, after trillions of years, it will quietly shed its outer layers and shrink into a white dwarf. Its end will be silent, gradual, and almost invisible compared to the fireworks of its ancient cousins. So here's the contrast in simplest terms. The massive stars were the sprinters of the cosmos, while SM0313 is the marathon runner. The sprinters blazed a trail and collapsed, while the marathon runner kept going, steady and tireless, surviving across epochs. Both were essential. Without the sprinters, there would have been no metals to form the next generations of stars, and without the marathon runners, we'd have no living fossils to study today. SM0313's quiet endurance is meaningful precisely because it is the counterpoint to those explosive giants. The massive stars ignited the first sparks of cosmic chemistry, and SM0313 preserved their story across nearly the entire age of the universe. When we describe SM0313 as extremely metal-poor, we're pointing to a profound truth about the cosmos itself. The early universe simply didn't have metals to begin with. To modern ears, that may sound odd. After all, metals are everywhere around us. The iron in your blood, the calcium in your bones, the oxygen you breathe, and the silicon in the device you're using right now, all of these are metals in the astronomer's definition. But in the earliest days of the universe, none of these existed. There was only the most basic matter, the most fundamental ingredients of existence. To understand why, we have to wind the cosmic clock all the way back to the Big Bang. In those first minutes after the universe burst into being, conditions were unimaginably hot and dense. Protons and neutrons fused together in a process called Big Bang nucleosynthesis. But this process had limits. It could only forge the lightest elements, mostly hydrogen, a smaller portion of helium, and trace amounts of lithium. And that was it. No carbon, no oxygen, no iron, no gold. This elemental simplicity defined the primordial universe. For perhaps the first 100 million years, The universe was a vast expanse of hydrogen and helium gas. It was dark, nearly featureless, and chemically barren compared to the richness we see today. In this environment, the very first stars, the population 3 stars, began to form. And here's the key point: those first stars were the factories that created the first metals. Inside their cores, nuclear fusion slowly stitched together heavier and heavier elements. A massive star might begin by fusing hydrogen into helium, then helium into carbon, then carbon into oxygen, and eventually on up the ladder toward iron. But those elements didn't become part of the wider universe until the star died. Only in its death throes, through a supernova explosion, were those heavy elements blasted out into space, enriching the surrounding gas clouds. So before any star had lived and died, there were no metals anywhere. The cosmic pantry was empty, stocked only with hydrogen, helium, and a pinch of lithium. This is why stars like SM0313, which formed incredibly early, have almost no metals at all. They were born before the universe had time to enrich itself. This makes SM0313's composition a kind of cosmic fossil record. Its near-total lack of iron isn't just an oddity, it's a reflection of the universe's first chemical steps. SM0313 came into being after only one or perhaps a few supernovae had gone off, meaning the gas cloud that birthed it was still nearly pristine. Its very existence proves that we are looking back at a time when the universe had only just begun to forge complexity out of simplicity. It also highlights the incredible transformation the cosmos has undergone. Fast forward 13.8 billion years to today, and we live in a universe rich in metals. Our Sun, for instance, is a population 1 star, born about 4.6 billion years ago from a heavily enriched gas cloud. It contains 1,000 times more iron than SM0313. The Earth itself, with its iron core, silicate crust, oceans of water, and complex chemistry, could never have formed in the early universe. It was only possible because generations of stars lived, died, and seeded the cosmos with metals. So when we ask why no heavy metals in the early universe, the answer is simple: because they hadn't been made yet. The universe had to wait for stars to cook them up and scatter them. Every atom of iron, carbon, oxygen, nitrogen, and beyond was forged in the heart of some ancient star. As the famous Carl Sagan line goes, we are literally made of star stuff, and SM0313 reminds us of the time before that process had really begun. That's what makes SM0313 so precious. It shows us a snapshot of the cosmic dawn, when the universe was still raw and unadorned, before stars seeded the richness that would eventually lead to galaxies, planets, and life. Its metal-poor nature isn't a deficiency, it's a clue, a signature, and a time marker etched in starlight. When astronomers gaze at SM0313, they aren't just admiring an ancient star, they're running one of the most important scientific experiments in existence. This star is not only a relic of cosmic history, it is also a test bench for our theories about the Big Bang and the universe's earliest chemistry. Let's start with the baseline, the theory of Big Bang nucleosynthesis. According to this model, during the first few minutes after the universe's birth, conditions were hot and dense enough to fuse subatomic particles into light atomic nuclei. The theory predicts a very specific outcome: about 75% hydrogen, 25% helium by mass, and only trace amounts of lithium and beryllium. Nothing heavier than that. This framework has been remarkably successful, confirmed by precise measurements of the cosmic microwave background and by the abundances of light elements observed in ancient gas clouds. But here's the problem: we can't travel back in time to directly sample the universe when it was only a few 100 million years old. What we can do, however, is look at ancient stars like SM0313, which preserve the chemical fingerprint of that era. SM0313 is effectively a cosmic laboratory, a time capsule containing information about what the universe looked like chemically just after the Big Bang. Its composition matches many predictions of Big Bang nucleosynthesis. For instance, the absence of iron and other heavy metals in SM0313 confirms that the universe began without these elements. That aligns with the idea that the first metals were forged only in the cores of stars that lived and died later. The very scarcity of metals in SM0313 is living proof that the first generation of stars must have been the ones to enrich the cosmos, because SM0313 itself shows none of that enrichment except in trace amounts. At the same time, SM0313 also challenges and refines our models. For example, while Big Bang nucleosynthesis predicts hydrogen, helium, and a touch of lithium, SM0313 also contains noticeable amounts of carbon, magnesium, and calcium. These cannot have come directly from the Big Bang. They must have been seeded by at least one earlier supernova. The presence of carbon, in particular, raises questions. Why so much carbon, and why almost no iron? This peculiar balance forces astrophysicists to revisit their models of the very first supernovae. Instead of assuming that all massive stars exploded symmetrically and spread their elements evenly, the evidence from SM0313 suggests that some early supernovae may have been faint explosions, ejecting lighter elements like carbon but trapping much of their iron within the collapsing remnant. This is where SM0313 shines as a test of theory. It isn't just confirming the broad strokes of Big Bang nucleosynthesis, it is helping to probe the fine details of early stellar evolution and chemical enrichment. By comparing SM0313's chemical fingerprint with theoretical models, astronomers can refine their understanding of how the first stars lived and died. Even lithium, which is predicted in small amounts by Big Bang nucleosynthesis, has sparked debate when studied in old stars like SM0313. Many ancient stars show less lithium than models predict, raising questions about whether early stars destroyed lithium in their interiors or whether the theory itself needs adjustment. SM0313 is one more critical data point in this ongoing puzzle. In short, SM0313 acts as both a confirmation and a challenge. Its extreme metal-poor nature confirms the idea that the early universe was chemically simple. But its peculiar mixture of carbon without iron forces us to rethink the details of how the first stars exploded. Without stars like SM0313, our theories would remain abstract equations and simulations. With it, we have a tangible object, a real star shining in our galaxy, that lets us check whether our cosmic story holds up. This is why astrophysicists sometimes refer to such stars as cosmic laboratories. Each one is like a data point in the grand experiment of existence, allowing us to test the predictions of cosmology and tweak them where reality doesn't quite match the theory. SM0313 reminds us that the universe is not only understandable but also testable, even across billions of years. When astronomers first studied SM0313's spectrum in detail, they were struck by something unexpected. This star, one of the oldest and most metal-poor ever discovered, wasn't entirely empty of heavier elements. In fact, it had a surprising abundance of carbon. That might sound like a small detail, but in the context of cosmic history, it's one of the strangest and most important features of this ancient relic. To appreciate why this is unusual, we have to return to the way elements are built in stars. In the nuclear furnaces of massive stars, fusion builds heavier elements step by step. Hydrogen fuses into helium, helium into carbon, carbon into oxygen, and eventually, through successive burning stages, up to iron. When the star explodes in a supernova, these elements are cast into space, enriching the interstellar medium. Usually, where there is carbon and oxygen, we also expect to find iron, because the fusion process that creates carbon and oxygen is linked, further down the chain, to the processes that produce iron. But SM0313 doesn't follow this expected pattern. It shows a clear excess of carbon, enough that astronomers call it a carbon-rich star, yet it is nearly devoid of iron. Its iron abundance is so low it's essentially undetectable, less than 1 part in a billion compared to the Sun, but its carbon content is relatively high. This mismatch is what makes SM0313 so peculiar. Why would the early universe produce a star that is carbon-rich but iron-poor? The leading explanation involves the peculiar nature of the first supernovae. One theory suggests that SM0313 was born from the debris of a faint supernova. In such an explosion, the outer layers of the star, rich in lighter elements like carbon, are blown into space, while much of the iron in the star's core collapses inward and is swallowed by the newborn neutron star or black hole. In other words, the explosion was incomplete or asymmetric, enriching the surrounding gas with carbon but leaving little to no iron behind. Another possibility is that the star's peculiar composition is the result of mixing and fallback. In this scenario, the first massive star exploded, but the explosion wasn't strong enough to eject all of its heavy elements. Instead, the innermost iron-rich material fell back onto the collapsed core, while only the lighter elements like carbon, magnesium, and calcium escaped into space. The cloud of gas that later condensed into SM0313 would therefore be carbon-rich but iron-poor. This carbon-rich nature has important implications for our understanding of the early universe. For one, it suggests that the first stars were not all uniform in the way they lived and died. Some of them may have had unusual fates, producing very different chemical fingerprints in their surroundings. SM0313's chemistry hints at this diversity. But there's another layer. The carbon in SM0313 might actually have been essential for the star's very existence. Astronomers think that in the early universe, the first stars formed in a very difficult environment. With only hydrogen and helium available, gas clouds couldn't cool easily, and cooling is essential for gravity to collapse a cloud into a dense star. Carbon and oxygen are highly efficient coolants. A gas cloud with even a trace of carbon could radiate heat away more effectively, allowing it to fragment into smaller clumps, small enough to form low-mass stars like SM0313. In other words, without carbon, SM0313 might never have formed at all. This is one of the great paradoxes of SM0313. Its carbon abundance makes it strange among the most metal-poor stars, but it may also be the very reason it has survived to the present day. It's a cosmic twist. The very element that makes it peculiar may also be what preserved it as a time capsule from the dawn of the cosmos. So, the carbon-rich but iron-poor nature of SM0313 is not just an oddity, it's a profound clue. It tells us that the first stars may have exploded in unusual ways, that early supernovae didn't always distribute their elements evenly, and that carbon played a critical role in enabling the formation of long-lived, low-mass stars. SM0313, with its strange chemical recipe, carries in its light the story of these first explosive events and the chemical quirks that shaped the universe's path forward. Astronomers often describe stars like SM0313 as chemical fossils, relics that preserve, in their very makeup, the story of long-vanished predecessors. But unlike bones or shells in a museum, this fossil is still burning, still alive, still speaking across nearly 14 billion years. Its odd mix of elements, carbon-rich but iron-poor, points back to a very specific kind of ancestor, a massive population 3-star that ended its life not with a grand, symmetrical explosion, but with something far stranger. This is where supernova models come in. The goal of these models is to simulate how the very first stars ended their lives and what kind of chemical footprints they left behind. For SM0313, the evidence points toward one very particular outcome, a faint supernova. In a standard core collapse supernova, a massive star, say 20 to 50 times the Sun's mass, burns through its nuclear fuel, eventually forming an iron core that can no longer support itself. When that core collapses, the outer layers are blasted away in a violent detonation, scattering iron and other heavy elements far and wide. If SM0313 had been born from such an event, we would expect to see at least some iron in its spectrum. But we don't. Instead, SM0313's near-total lack of iron suggests that the explosion didn't behave in the usual way. The faint supernova model provides a neat explanation. In this scenario, the explosion was weak and asymmetric. The outer layers of the dying population 3-star, containing lighter elements like carbon, magnesium, and calcium, were blown into space. But the iron-rich inner layers never escaped. Instead, they fell back onto the collapsing remnant, feeding the black hole or neutron star left behind. Astronomers call this process mixing and fallback. The result is an environment enriched in lighter elements but starved of iron, exactly the kind of gas cloud from which SM0313 must have formed. The fact that SM0313 exists at all suggests that faint supernovae were not rare. If every population 3-star had exploded in a powerful, iron-rich burst, the first generations of surviving stars would all have shown much higher metallicities. Instead, SM0313 tells us that at least some of those first giants died quietly, ejecting only part of their chemical bounty into the cosmos. Other supernova models have also been proposed. For instance, some researchers suggest that jet-driven supernovae, explosions where matter is ejected along narrow beams rather than evenly in all directions, could produce the same unusual chemical pattern. In such cases, lighter elements like carbon could be sprayed outward while heavier elements remain trapped. Others argue for asymmetric explosions, where only certain layers of the star are expelled into space, depending on the energy of the blast. The common thread across these models is that SM0313's chemical fingerprint could not have come from a normal supernova. Its odd balance requires something faint, unusual, or incomplete. That's what makes this star so valuable. It forces astrophysicists to refine their theories of how the very first stars lived and died. And there's more. These models don't just explain SM0313, they also connect to the larger puzzle of how the early universe evolved. If faint supernovae were common, it means that the first generations of stars did not enrich their surroundings as quickly as once thought. That would delay the buildup of metals in galaxies and stretch out the period when stars like SM0313 could form. In other words, SM0313's chemical story may also be telling us about the timeline of cosmic chemical evolution. Imagine it, a lone star in the halo of our Milky Way, whispering the tale of a long-dead giant that exploded weakly, seeding the universe with just enough carbon for new stars to form. SM0313's light carries across billions of years the memory of that event, allowing us to reconstruct one of the earliest chapters in the story of creation. Why do astronomers devote so much effort to finding stars like SM0313? After all, it's not the brightest star in the sky. It doesn't dazzle with spectacular flares or exotic phenomena like neutron stars or black holes. By most casual measures, it's quiet, faint, and almost unremarkable. But in truth, stars like SM0313 are some of the most precious finds in the entire field of astronomy. They matter because they are among the best observational windows into the early cosmos. Let's imagine the problem that cosmologists face. We want to understand what the universe was like right after the Big Bang, how galaxies formed, how stars first lit up the darkness, and how the chemical elements we know today slowly came into existence. But the universe doesn't exactly give us an easy way to peer back that far. The light from the very first stars has long since vanished. Those population 3 giants lived short, furious lives and left no direct survivors. What's left behind are traces, whispers of their existence written into the chemistry of the second generation of stars. That's where SM0313 comes in. SM0313 and other ultra-metal-poor stars act like time capsules. They preserve the chemical fingerprints of the universe only 100 or 200 million years after the Big Bang, a time we cannot otherwise observe directly. Their atmospheres lock in these ancient patterns, untouched by later processes, because such low-mass stars barely stir their outer layers. What we see in their spectra is essentially a frozen record of the conditions from which they were born. This is what makes them irreplaceable. Most stars we study, including our own Sun, are noisy mixtures of countless generations of stellar deaths. By the time a population 1 star like the Sun formed, the galaxy was already heavily enriched with iron, nickel, silicon, and dozens of other elements forged in the cores of earlier stars. Its composition is a cocktail of many ancient supernovae. By contrast, stars like SM0313 are like a clear, undiluted note in the symphony. 1 star, 1 supernova, 1 chemical fingerprint. That purity allows astronomers to reconstruct the earliest steps of cosmic history with far greater precision. The rarity of these stars also speaks to their importance. Among the hundreds of billions of stars in the Milky Way, only a handful are known with such extreme metal deficiencies. Each discovery is like uncovering a missing page from a nearly lost book of the universe's origins. SM0313 isn't just another star to catalogue. It's a singular, priceless relic that expands the limits of what we know about early stellar formation and chemical enrichment. And there's another reason why rare stars like SM0313 matter. They provide crucial tests of theory. Cosmologists and nuclear. Physicists build detailed models of Big Bang nucleosynthesis, the first supernovae, and the buildup of elements across cosmic time. But without observational evidence, these models remain speculative. When we find stars like SM0313, we can compare their actual spectra to the predictions of our models. If the two align, we gain confidence in our understanding. If they don't, as often happens, the models must evolve. In this way, each rare star acts as a referee between theory and reality. There's also a poetic element to why these stars matter. They connect us directly to the dawn of everything. SM0313 is not just an old star. It's a survivor that has witnessed the rise of galaxies, the birth of countless stars, and nearly 14 billion years of cosmic evolution. And yet, It still burns quietly in the halo of our galaxy, waiting to be discovered by curious eyes on a small blue planet. There's a humbling quality to that thought. This faint star existed long before Earth was born, long before our Sun, and it will likely keep shining long after our world has faded. In short, rare stars like SM0313 matter because they are the only natural laboratories we have to study the conditions of the universe's earliest epochs. They are not just stars, they are keys to time itself. Without them, our picture of the early cosmos would be guesswork. With them, we gain hard evidence, concrete data, and a direct line of sight back to the first moments when the universe transitioned from darkness to light. Hunting for stars like SM0313 is one of the greatest challenges in modern astronomy. Not because these stars don't exist, we know they do, but because they are so incredibly rare, faint, and hidden among the countless other stars in the Milky Way. Finding one is a little like combing through every grain of sand on a vast beach, hoping to spot a single grain that looks ever so slightly different from the rest. To understand why it's so difficult, we need to picture the scale of the galaxy. The Milky Way contains somewhere between 200 and 400 billion stars. Most of them are ordinary population 1 and population 2 stars, enriched with varying amounts of metals from previous generations. Buried within this enormous population are just a handful of ultra-metal-poor stars, relics like SM0313. Out of hundreds of billions, astronomers have found only a few dozen with metallicities this low, and SM0313 remains among the most extreme. That already makes the search like looking for the faintest echo in a stadium full of noise. Then there's the matter of brightness. Stars like SM0313 are generally low-mass stars, which means they don't shine nearly as brightly as massive, short-lived stars. Their faint light is further dimmed by distance, since they typically dwell in the galactic halo, tens of thousands of light-years away from Earth, orbiting far above and below the bright plane of the Milky Way. As a result, they appear as tiny, dim pinpricks, almost indistinguishable from the background clutter of stars. On top of that, we have the issue of distinguishing them spectroscopically. To tell whether a star is metal-poor, astronomers need to take its light and spread it into a spectrum, carefully analyzing the absorption lines of different elements. That requires sensitive instruments and long observing times, especially for faint stars. Most large surveys cannot afford to spend hours studying every dim halo star in detail. Instead, astronomers have to use clever filtering methods, identifying likely candidates before committing precious telescope time to follow-up observations. This is where projects like SkyMapper in Australia, which first detected SM0313, come into play. SkyMapper was designed to scan large areas of the sky quickly and to identify stars with unusual color signatures that hint at low metallicity. Even then, only a small fraction of the candidates turn out to be truly metal-poor when studied with powerful spectrographs. In SM0313's case, its extreme faintness and the almost complete lack of ion lines in its spectrum made it leap out once follow-up spectroscopy was done. But getting to that point required sifting through an immense ocean of stars. Another difficulty is that these stars are relics, and as such, they often lurk in remote regions of the halo where star density is sparse. Unlike stars in the galactic disk, halo stars are more widely scattered, meaning astronomers can't simply look in a dense cluster and expect to find one. The halo is vast, extending far beyond the main visible disk of the Milky Way, so mapping it is a slow and painstaking effort. And even when a promising star is located, the work doesn't stop. Extracting its chemical story requires the world's largest telescopes, instruments like the Very Large Telescope, VLT, in Chile or the Keck Observatory in Hawaii, which can collect enough light to analyze faint stars in exquisite detail. Such telescope time is highly competitive, with astronomers around the world vying for precious hours. To justify studying a faint halo star like SM0313, the case has to be compelling. All of this adds up to a monumental task. Finding one ultra-metal-poor star can take years of work, multiple survey instruments, and international collaborations. Each discovery is a triumph of persistence, data analysis, and technology. And it underscores just how extraordinary SM0313 really is. Not only is it rare by nature, but it's also rare by circumstance, one of the very few stars of its kind we've been able to uncover despite the odds stacked against us. In some sense, the difficulty of finding stars like SM0313 adds to their value. Their rarity and elusiveness make them treasures when finally uncovered, jewels of the cosmic fossil record. Every one that is discovered sharpens our picture of the early universe and validates the years of effort poured into galactic archaeology. If you've ever seen an archaeologist brushing away layers of dirt to uncover ancient pottery or bones, you already have a metaphor for what astronomers do when they practice galactic archaeology. But instead of digging into the ground, galactic archaeologists dig into the sky, uncovering the oldest and most pristine stars in the Milky Way to piece together the story of our galaxy's formation and evolution. Galactic archaeology is a relatively new but increasingly important field of astrophysics. Its goal is simple in concept but profound in scope: to use stars as fossils, each one carrying chemical records of the time and place where it was born. Just as human archaeologists reconstruct civilizations by studying ruins and artifacts, galactic archaeologists reconstruct the history of the Milky Way by studying its stars, especially the ancient ones like SM0313. The logic behind this field is elegant. Stars lock away in their atmospheres the chemical composition of the gas cloud from which they formed. That chemical composition acts as a timestamp. A star rich in heavy elements almost certainly formed later in the galaxy's history, after countless generations of supernovae had seeded the interstellar medium with metals. By contrast, a star with nearly no metals, like SM0313, must have formed in the very early universe, before metals were widespread. In this way, the chemical fingerprint of a star tells astronomers when it was born and what sort of cosmic environment existed at that time. Galactic archaeology also pays attention to where stars are found. The Milky Way is not a uniform structure. It has a thin disk, a thick disk, a central bulge, and an extended halo. Stars in the thin disk, like our Sun, are relatively young and metal-rich. Stars in the halo, however, tend to be ancient, metal-poor, and scattered widely. By mapping the distribution and chemistry of halo stars, astronomers can reconstruct how the Milky Way grew, through mergers with smaller galaxies, through bursts of star formation, and through the gradual buildup of chemical elements. SM0313 is a perfect subject for galactic archaeology because it acts like a pristine fossil. It belongs to the halo, it is extremely metal-poor, and its chemical fingerprint points to the influence of a single first-generation supernova. In other words, it provides a direct glimpse into what the galaxy's first layer of history looked like. Without stars like SM0313, galactic archaeologists would be trying to write the early chapters of the Milky Way story without any evidence. With it, they can place real constraints on how quickly metals spread, how early stars lived and died, and how the galaxy began assembling itself. One of the exciting aspects of galactic archaeology is that it is inherently interdisciplinary. It brings together cosmology, the study of the universe as a whole, stellar physics, understanding how stars evolve and produce elements, and galactic dynamics, how stars move and interact in the Milky Way. It also depends heavily on cutting-edge technology. Massive sky surveys like SkyMapper, Gaia, and SDSS provide the raw data, while powerful spectrographs on giant telescopes extract the chemical details. Without this combination of theory, observation, and technology, the field wouldn't exist. It's also worth noting that galactic archaeology is open-ended. Unlike digging up a pyramid, where you eventually reach the bottom, the galaxy always offers more stars to study, more fossils to find, more relics hidden in its halo. Every time a new ultra-metal-poor star is discovered, the field gets another data point, another fragment of the Milky Way's ancient puzzle. Some stars show signatures of unusual supernovae, others hint at the presence of faint galaxies long ago consumed by the Milky Way. Together, these discoveries are weaving a tapestry of galactic history that's richer and more detailed than ever before. Perhaps the most poetic part of galactic archaeology is this: by studying stars like SM0313, we are not only reconstructing the Milky Way's history, we are also indirectly reconstructing our own. After all, the chemical evolution that these ancient stars reveal eventually led to the creation of the Sun, the Earth, and the elements inside our bodies. Galactic archaeology tells us not just how the galaxy formed, but also how the raw ingredients of life itself came to be. SM0313, then, isn't just an object of curiosity. It's a cornerstone of galactic archaeology, a fossil that helps define the earliest chapter of our galaxy's long, complex story. When we talk about ancient stars like SM0313, it's natural to wonder, is it the only one? The short answer is no. Over the decades, astronomers have uncovered a small but fascinating group of stars that are among the oldest in the universe, and comparing them helps us sharpen our understanding of cosmic history. Among these contenders, one of the most famous is HD 140283, widely nicknamed the Methuselah star. The Methuselah star earned its nickname for good reason. Early studies suggested it might be as old as 14.5 billion years, which posed a real problem, since the universe itself is about 13.8 billion years old. Clearly, something had to be off. Later refinements in stellar modeling brought its estimated age down to around 13.6 to 13.7 billion years, more in line with cosmological limits. Still, even with uncertainties, it remains one of the oldest stars ever measured. Unlike SM0313, however, HD 140283 is relatively close to us, only about 200 light-years away in the constellation Libra, and it's bright enough to be seen through small telescopes. At first glance, you might think HD 140283 is just as valuable as SM0313 in tracing the early universe, but there are important differences. The Methuselah star, while old, is not nearly as metal-poor as SM0313. It does contain iron and other heavy elements, just in very low amounts compared to the Sun. In fact, HD 140,283's metallicity is about 1/250th that of the Sun, extremely poor by everyday standards, but still vastly richer than SM0313, which is less than 1 part in a billion the iron content of the Sun. In other words, HD 140283 belongs to a later wave of early stars, whereas SM0313 is chemically closer to the very dawn of star formation. Other contenders for the title of oldest star include E1523-0901, found in 2007 and dated to about 13.2 billion years, and BD plus 17°3248, another halo star with an age estimate over 13 billion years. These stars, like HD 140283, are remarkable in their longevity and their usefulness for refining age dating methods, but again, none exhibit the extreme chemical simplicity of SM0313. That's where the contrast lies. Stars like HD 140283 are invaluable for measuring cosmic timescales, while stars like SM0313 are invaluable for decoding cosmic origins. The Methuselah star tells us about the stability and lifespan of ancient stars, anchoring the lower bound of stellar ages. But SM0313 tells us about the first supernovae, the earliest chemical enrichment events, and the conditions of the infant universe. Where HD 140283 is a survivor from the early days of the Milky Way's disk and halo, SM0313 is a direct messenger from the primordial universe itself. We might think of it like this: the Methuselah star is an elder statesman of the galaxy, ancient, wise, and enduring, but still touched by a history already in progress. SM0313, by contrast, is more like an artifact from before history properly began, a relic from a time when the universe was just learning how to make stars at all. This comparison highlights a subtle but crucial point: oldest is not a simple label in astronomy. Age is one factor, but chemical composition adds an entirely different dimension. A star might be almost as old as the universe, but if it contains metals, it must have formed after at least some supernovae had already seeded the cosmos. SM0313's near-pristine composition suggests it was born almost immediately after those very first events. That makes it unique, even among the Methuselah-like stars. So while HD 140283 and others remain pillars of age dating in astrophysics, SM0313 stands apart as a star that's not just ancient, but primal. It is as close as we've come to touching the ashes of the very first stars, and that is a distinction that makes it one of the most extraordinary stellar discoveries in human history. The discovery of SM0313 in 2014 was just the beginning of its story. Finding such a rare and ancient star lit a fire in the astronomical community, and since then, researchers have been relentless in their pursuit to uncover every possible detail about it. After all, a star this old, one that may have formed only 100 to 200 million years after the Big Bang, is not just an object to catalogue. It is a cosmic laboratory. Every spectrum, every analysis, every photon that reaches Earth carries secrets about the conditions of the infant universe. To unlock those secrets, astronomers have turned to some of the most powerful tools ever built by humanity, including the Very Large Telescope, VLT, in Chile and, more recently, the James Webb Space Telescope, JWST. Let's start with the VLT. Located high in the Atacama Desert, one of the driest, clearest skies on Earth, the VLT is a cluster of 4 massive telescopes, each with an 8.2-meter mirror. Its instruments are especially good at one thing: breaking down starlight into its spectrum. This is vital for studying stars like SM0313, because the key to its importance lies in what elements appear, or don't appear, in its light. Shortly after its discovery, astronomers used the VLT to conduct ultra-high-resolution spectroscopy of SM0313. What they found confirmed its bizarre and unique nature: an almost complete absence of iron, yet detectable amounts of carbon, calcium, and magnesium. The VLT didn't just confirm its strangeness, it also helped refine its story. By carefully analyzing the chemical fingerprint of SM0313, astronomers could test different models of how the gas cloud it was born from might have been enriched. One leading explanation is that a single faint supernova, an explosion so weak that most of its heavy elements fell back into the remnant rather than dispersing into space, seeded the material from which SM0313 formed. The VLT data supported this picture, making SM0313 a textbook example of how the earliest supernovae shaped the chemical landscape of the cosmos. But as extraordinary as the VLT is, it still has its limits. That's where the JWST enters the story. Launched in late 2021 and stationed nearly 1 million miles from Earth at the L2 point, JWST is optimized for infrared observations. Why does that matter? Because many of the absorption lines that reveal the presence of certain elements in stars are faint and often easier to detect in the infrared spectrum. JWST also has the advantage of observing from space, free from the distortions and absorption caused by Earth's atmosphere. Although JWST's primary mission includes studying the earliest galaxies and exoplanet atmospheres, it is also a game-changer for stellar archaeology. For stars like SM0313, JWST can probe for even subtler chemical fingerprints than ground-based telescopes can detect. For example, it might reveal traces of nitrogen or oxygen that are otherwise undetectable from Earth. Such data could dramatically refine our understanding of what kind of supernova enriched SM0313's birth cloud. Was it truly a faint supernova, or could it have been an exotic explosion type we have not yet fully modeled? JWST's sensitivity may finally provide the answer. In addition to chemical details, JWST and future observatories could help pin down precise ages. Right now, estimates of SM0313's age rely on models of stellar evolution and assumptions about its metallicity. By combining JWST's observations with data from Gaia, which maps stellar motions and positions with unprecedented accuracy, astronomers can better constrain not just SM0313's chemistry but also its dynamics. How it orbits the Milky Way, where it might have originated, and whether it was part of a smaller galaxy long ago absorbed into the Milky Way's halo. And the research does not stop with JWST. Next-generation ground-based giants, such as the Extremely Large Telescope, ELT, currently under construction in Chile with a 39-meter mirror, will push the boundaries even further. With its enormous light-gathering power, the ELT will be able to collect detailed spectra of faint stars like SM0313 much faster and with much higher precision. This will open the door to detecting more ultra-metal-poor stars and comparing their compositions, giving astronomers a larger sample size of cosmic fossils to work with. The ongoing research into SM0313 is not just about understanding one star. It's about anchoring our models of the early universe. Every new measurement either strengthens or challenges current theories about how the first stars exploded, how metals spread through space, and how the next generations of stars took shape. SM0313 is a Rosetta Stone for cosmic history, and telescopes like the VLT, JWST, and soon the ELT are the translators helping us decode its ancient language. And yet, as much as these instruments have already revealed, SM0313 continues to guard some of its secrets. Even with our best technology, we can't yet say with certainty exactly what kind of progenitor supernova preceded it, or whether it truly represents the earliest possible stars after the Big Bang. That is the essence of science. Every answer opens up new questions. Every breakthrough expands the frontier of mystery. Despite all the progress astronomers have made in studying SM0313, it still stands before us like an ancient manuscript with missing pages, partially translated, yet leaving enormous gaps that challenge our imagination. For every fact we've uncovered, new questions seem to sprout in its place, reminding us that the cosmos is not a solved puzzle but an ongoing mystery. SM0313 is one of the clearest windows we have into the primordial universe, but even this window is fogged in places, obscuring details that we are still struggling to decipher. The first and perhaps most pressing question is, was SM0313 enriched by just one supernova, or multiple events? Current models lean heavily toward the idea that a single faint supernova seeded the gas cloud that birthed SM0313. This faint explosion would have produced abundant light elements like carbon and magnesium while trapping most of its heavier elements in the stellar remnant, explaining SM0313's odd signature, carbon-rich, iron-poor. But is that the full story? It's possible that SM0313 formed in a region touched by the ashes of more than one star, each contributing slightly different ingredients to the chemical soup. If so, then its unusual abundance pattern is not the fingerprint of one specific star's death, but rather a chorus of early explosions whose combined notes we are still trying to disentangle. This leads to the second question. Could SM0313 be directly connected to the very first stars, the so-called population 3 stars? Population 3 stars are purely theoretical. None have ever been directly observed. They are thought to have been massive, short-lived, and composed only of hydrogen and helium, the raw materials created by the Big Bang. If SM0313 formed from the ejecta of such a star, then it is effectively a second-generation witness to their existence. Its chemistry may be the only surviving record of a population 3 star's life and death. But which kind of population 3 supernova was it? A faint one? A pair instability supernova, which could completely unbind a star? Or something else altogether? Without more data, this remains speculative, but tantalizingly so. Another open question is how exactly SM0313 survived for so long. We know that its low mass is the key, since small stars burn their fuel slowly and live for billions of years. But how did such a low-mass star form at such an early time, when the universe's chemistry was so simple and cooling mechanisms for gas clouds were limited? Normally, heavier elements help gas clouds radiate away energy, allowing them to fragment into smaller stars. Without metals, the first stars are thought to have been massive. So how did a fragile, low-mass star like SM0313 manage to take shape in such an environment? This is one of the great paradoxes of its existence, and solving it may force us to rethink our models of early star formation. There is also the lingering uncertainty about hidden elements. So far, we know that SM0313 is almost devoid of iron but rich in carbon, magnesium, and calcium. But are there trace amounts of other elements lurking beneath the detection limits of current instruments? Could tiny amounts of nitrogen, oxygen, or even heavier metals be present, waiting for JWST or the future ELT to reveal them? Each new element detected, or absent, refines our understanding of what type of explosion seeded SM0313's birth cloud. We must also ask, where did SM0313 originally come from? Today, it resides in the halo of the Milky Way, but halo stars often trace their origins back to smaller galaxies that merged with ours billions of years ago. Could SM0313 have once belonged to a dwarf galaxy, one of the Milky Way's many swallowed companions? If so, then not only is it a relic of the early universe, but also a relic of an ancient galactic ecosystem that no longer exists. Its orbit, which we can now trace thanks to Gaia, may hold the key to this mystery. Finally, the most profound question of all remains unanswered. Is SM0313 truly unique, or is it just the first of many? If we find more stars like it, we'll know that this was not a one-off anomaly but part of a broader pattern of early cosmic evolution. But if SM0313 remains alone, then we may be looking at a 1 in a billion survivor, a single star that has outlasted time itself to bring us a message from the dawn of creation. What we don't yet know about SM0313 is, in some ways, even more exciting than what we do. Each mystery is a doorway, each uncertainty an invitation. Perhaps one day, with the help of telescopes yet to be built and models yet to be written, we will step fully through those doorways and finally grasp the full story of this ancient star. Until then, SM0313 reminds us that science is not just about answers, but about the pursuit of questions that stretch our minds to the edges of the universe. The story of SM0313 does not end with its own existence. In fact, its significance extends far beyond the confines of stellar astrophysics, reaching into the most profound question humanity has ever asked. How did life come to be? To appreciate the connection between this ancient star and our own existence, we must step back and think of the universe not just as a vast expanse of stars and galaxies, but as a cosmic evolutionary process. SM0313, with its near-pristine chemistry, stands as a marker in that process, a witness to a time before the universe had the ingredients necessary to build planets, oceans, DNA, and eventually, us. When the Big Bang occurred 13.8 billion years ago, it produced primarily hydrogen, helium, and a trace of lithium. That was it. No carbon for organic molecules, no oxygen for water, no silicon for rocky planets, no iron for blood and magnetic cores. The early universe was a chemically barren landscape. If you tried to build a planet or a living organism with only hydrogen and helium, you'd fail. There simply wasn't enough complexity in the elemental toolkit. That's why the first generations of stars, including population 3 and early population 2 stars like SM0313, were so critical. They were the cosmic forges. Through nuclear fusion, stars convert lighter elements into heavier ones: carbon, nitrogen, oxygen, silicon, calcium, and eventually iron. When these stars died, often in violent supernovae, they scattered their newly minted elements into the cosmos, enriching the interstellar medium. Over time, this cosmic recycling transformed the universe from a simple soup into a chemical smorgasbord, ready to build complex structures. SM0313 fits into this story as a kind of control sample. Because it is so poor in heavy elements, it shows us what the universe looked like before this enrichment process was well underway. In a sense, SM0313 is the before picture in the cosmic chemical makeover. By studying it, astronomers can see the precise point in history where the transition began, when the first stars had died, but the universe had not yet been filled with the ingredients that would one day build solar systems like ours. And here's the astonishing implication. Without stars like SM0313 and the supernovae that preceded it, life as we know it could never have existed. The carbon in your body, the oxygen in your lungs, the calcium in your bones, the iron in your blood, all of it was forged in stars and spread through ancient explosions. You are, quite literally, made of star stuff, as Carl Sagan so eloquently put it. SM0313 is a reminder of that truth. Its very scarcity of metals tells us that the cosmos had to go through a long, patient process of element building before life became possible. Think of it like this: if the universe were a story, SM0313 would appear in Chapter 1, a character from the prologue, before the real drama of planets and biology even began. But without that early chapter, the later story would make no sense. By examining SM0313, we trace the roots of the evolutionary tree of matter that eventually blossomed into life. Another key point lies in timing. SM0313's formation within 100 to 200 million years after the Big Bang shows us how quickly the cosmic element cycle began. Within just a few hundred million years, the universe was already experimenting with star formation, supernova explosions, and the slow buildup of chemical diversity. This early start was crucial. If the first stars had formed much later, or if their explosions had been less efficient at seeding space with metals, the timeline for galaxy and planet formation could have been pushed back significantly. Life on Earth might never have had the billions of years it needed to evolve. SM0313 also highlights a paradox. Though it is too metal poor to have ever hosted planets or life in its immediate environment, its existence is directly tied to the process that made life possible elsewhere. It is like a fossil of a creature that lived before ecosystems existed, yet its very survival paved the way for ecosystems to emerge later. It's a cosmic irony. The stars least likely to support life in their own systems may be the most important for making life possible across the universe. This leads to a profound philosophical reflection. Looking at SM0313 is, in a sense, looking back at the preconditions of our own existence. It is humbling to realize that the oxygen we breathe and the carbon in our cells were impossible when this star was born. We had to wait billions of years, through countless cycles of star birth and death, for the universe to build the raw ingredients of biology. Stars like SM0313 remind us that life is not just a biological phenomenon, It is the endpoint of a cosmic chemical journey that began in the first seconds after the Big Bang. So the implications for life are immense. By studying SM0313, we gain not just a window into astrophysics, but a mirror that reflects our own origins. It tells us that life is woven into the fabric of cosmic history, not inevitable, but deeply rooted in the long, slow alchemy of stars. Every breath we take is a testament to explosions that happened long before Earth was even a dream. SM0313 is proof of that journey, a silent witness that still burns today, reminding us where we came from. When we think about SM0313, it's tempting to see it as a cosmic loner, an isolated relic, a one-of-a-kind survivor from the dawn of time. But one of the most thrilling aspects of modern astronomy is that it forces us to consider the possibility that SM0313 is not unique at all. Instead, it may be the first clear example of a hidden population of ancient stars, scattered across the Milky Way and perhaps even beyond, each one carrying a fragment of the universe's earliest history. And finding them, if we can, may completely rewrite our understanding of how our galaxy formed, how chemical enrichment unfolded, and how the universe evolved in its first billion years. The search for other stars like SM0313 is more than a matter of curiosity. It is a scientific imperative. Astronomers often describe such stars as fossils of the early universe. Just as paleontologists piece together Earth's ancient history from fossilized bones, galactic archaeologists use stars like SM0313 to reconstruct the cosmic past. One fossil is fascinating, but a whole collection tells a story. With more discoveries, we can begin to map the patterns, see the variations, and understand the broader picture of star formation in the primordial cosmos. Future discoveries are highly likely because of one simple truth: the Milky Way is vast. Our galaxy contains somewhere around 200 to 400 billion stars, many of them ancient. Even if only a tiny fraction are as metal-poor as SM0313, that still means millions could exist. Most are simply too faint, too distant, or too hidden in the galactic halo to have been identified yet. But with new telescopes and advanced surveys, we are beginning to peel back the layers of the galaxy and spot more of these rare treasures. Telescopes like the European Southern Observatory's Very Large Telescope, VLT, have already proven their worth by confirming SM0313's properties. But the future lies with next-generation instruments such as the James Webb Space Telescope, JWST, the Vera C. Rubin Observatory with its massive legacy survey of space and time, LSST, and the forthcoming Extremely Large Telescope, ELT. These observatories will allow astronomers to survey the sky with unprecedented depth and precision. JWST, for example, is already capable of examining faint galaxies from the first few 100 million years after the Big Bang. If it can do that across billions of light-years, imagine how effectively it can hunt down faint, ancient stars in our own galactic backyard. Each new discovery of a star like SM0313 would add a crucial puzzle piece. By comparing the chemical signatures of different extremely metal-poor stars, astronomers can test models of early supernova explosions. Did faint supernovae dominate, as SM0313 suggests? Or did multiple types of explosions leave their fingerprints across the halo? With a sample of dozens or hundreds of such stars, we could trace the diversity of the first stellar deaths and refine our picture of the earliest universe. These stars may also reshape our view of the Milky Way's formation. Our galaxy is not a static structure. It is a product of countless mergers and accretions. The halo, where SM0313 resides, is thought to be built largely from smaller galaxies swallowed by the Milky Way billions of years ago. If we can map the chemical fingerprints of many stars like SM0313, we may be able to trace which stars were born in the Milky Way itself and which were imported from ancient galactic collisions. In this way, extremely metal-poor stars are not only fossils of the early universe but also clues to the genealogy of our own galaxy. There's also the possibility of finding even older, even purer stars. SM0313 is unusual in that it still shows some elements: carbon, magnesium, calcium. But what if astronomers discover a star with no detectable metals at all, one that might actually be a direct survivor from the population 3 generation? Such a discovery would be earth-shattering, offering the first direct observation of the first stars. Many experts suspect these stars are either too rare or too faint to be found, but as telescope technology pushes deeper, what once seemed impossible begins to feel plausible. The discoveries won't just be limited to the Milky Way, either. Neighboring dwarf galaxies, such as the Sculptor or Fornax dwarf spheroidals, are prime hunting grounds. These smaller galaxies often retain ancient stars that escape the cycles of enrichment that took place in larger galaxies. In fact, some astronomers suspect that the oldest, most pristine stars may be easier to find in dwarf galaxies than in the Milky Way itself. The impact of finding more stars like SM0313 would ripple far beyond astrophysics. It would deepen our understanding of cosmic chemical evolution, helping refine the timeline of when the universe became hospitable to planets and, ultimately, life. It would help confirm or challenge Big Bang nucleosynthesis models. And it would push us closer to answering one of astronomy's ultimate questions. What were the very first stars like? But perhaps the most poetic implication of future discoveries is that they would show us we are not looking at a single ancient survivor, but rather listening to a chorus of voices from the dawn of time. Each star would be a different note in the universe's earliest song, and together they would form a symphony of history that has been playing for nearly 14 billion years. So, as extraordinary as SM0313 is, it may not be the last. It may be only the beginning of a new golden age in galactic archaeology. As technology advances and our gaze sharpens, we will likely uncover more of these ancient witnesses. And with each one we find, the early chapters of the cosmic story will become clearer, richer, and more complete. When we arrive at the end of SM0313's story, at least the part we are capable of telling today, we are left not just with data and theories, but with a profound sense of awe. Think about what this star represents. For nearly 13.6 billion years, it has burned steadily in the vast darkness of space. It was born when the universe itself was still in its infancy, when galaxies were only beginning to take shape, when the first generation of stars had only just ended their brief, violent lives. And yet, through all of that cosmic turmoil, through eons of galactic collisions, supernovae, and the endless dance of celestial evolution, SM0313 has survived. It is still there. It is still shining. It is still whispering its secrets into the instruments of the astronomers who search the night skies. To call it a relic is not quite enough. SM0313 is a living relic. Fossils on Earth are silent. They are imprints of a world long gone. But this star is still burning, still emitting light across the void, still tracing its ancient orbit around the Milky Way's halo. Every photon that reaches us from SM0313 has traveled thousands of years to get here, carrying with it a fragment of a story that began just after the birth of time itself. In that sense, when we look at SM0313, we are not just looking at a star. We are looking at an eyewitness of creation. It reminds us how fragile, yet how enduring, the universe can be. Massive stars, brilliant, short-lived, ferocious, came and went in the blink of a cosmic eye. But this faint, low-mass survivor, overlooked by the grand spectacle of supernovae, quietly endured. It outlived almost everything else from its time, and in doing so became a beacon, a messenger from the past. There's something deeply humbling in that, the idea that the universe entrusted some of its oldest memories not to the most powerful stars, but to the quietest ones. And so we find ourselves, on a small planet orbiting a middle-aged star, able to study SM0313 and reconstruct the earliest chapters of the cosmos. This is the very definition of cosmic perspective. Our species, which has only existed for the briefest sliver of time compared to SM0313's life, has developed the ability to decode its light, to read the patterns etched in its spectrum, and to extract from it the story of the universe's beginning. That, in itself, is an astonishing achievement, a reminder that in the grand narrative of the cosmos, consciousness and curiosity also have their place. SM0313 teaches us that the universe is not just vast, but layered with memory. Its light carries with it the echoes of the first stars, the first supernovae, the first heavy elements ever forged. Without stars like SM0313, we might never have pieced together how the cosmos evolved from a sea of hydrogen and helium into a galaxy-spanning ecosystem capable of producing planets, oceans, and life. Every moment that this star continues to shine is another moment that the universe keeps open its window into the past. Perhaps the most moving thought of all is this: SM0313 is not eternal. One day, far in the future, even it will exhaust its fuel. It will fade into a white dwarf and eventually cool into darkness. But right now, In our time, we exist in the rare overlap when this ancient star and our young species can meet. We are alive at the same moment that one of the universe's first survivors still glows. That coincidence is a gift, a reminder that in the immensity of space and the enormity of time, we are still connected to the very beginning. So when we gaze up at SM0313, or even when we simply reflect on its existence, we are reminded that we live in a universe where time stretches nearly 14 billion years into the past, and yet fragments of that earliest era still burn in the night sky. It is not just astronomy, it is poetry written in starlight. SM0313 is, in every sense, a time traveler, a cosmic storyteller, and a living relic of the dawn of creation. Its light is older than every planet, every mountain, every tree, and every breath of air on Earth. And yet, against all odds, it still shines, a solitary flame from the first chapter of the universe, still burning after nearly 14 billion years. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.